You're listening to Electrician Live with your host, Paul Abernathy. Well, hey everybody, welcome to another exam prep session. My name's Paul Abernathy. If you haven't joined us before, welcome to the stream. Again, we're streaming only tonight on YouTube. We're not going to stream on the Facebook tonight. Only going to stream on here. Okay, so thanks for joining us tonight, and hopefully you bought your code books and you are ready to do some optional methods, or at least ask questions. You got questions you need them asked, ask the questions. We'll try to answer them. Hopefully my shirt is not too bright. Back to the orange shirt. 12 Mandingos is in the house. Whoop, whoop. I don't have any raise the roof noises, but thanks for joining the stream. And welcome everybody. I'll give a few minutes here for people to fill in that are going to come. If you're going to come, maybe we don't. There's others that don't want to learn exam prep, or maybe optional methods isn't important to them. And okay. As we look at optional methods tonight, keeping in mind that typically on an exam, you're going to have most of your questions are probably going to be standard method. It's probably more often than not, that's what your exam questions are going to be about. And we have done a, what's up, Tim? Welcome to the stream. We have a presentation. I think I've done a standard calculation method training class on that as well. So again, we're doing exam prep on this, so everything kind of revolves around exam prep, whether we're looking up code questions or we're doing some, random calculations or whatever we're doing. We're just kind of doing them. Okay. Standard methods, what you use to get the neutral. Even when you spell neutral correctly, that's what you've got to use to do to do the neutral. Okay, so we're going to talk optional method tonight, but we talk about sizing neutral and we talk about the standard method in a previous episode that we've done. So today we're going to kind of look a little bit at optional methods. You never know when you're going to get a question about optional method. And the reality is, we want to make sure that you understand how to do it as well, because the optional method's probably going to be the method that you're going to use the most in the field. I think in all my years in this industry, I probably, most all calculations I've done is going to is results from the optional method. With that in mind, you have to know how to do the standard method, because you do have to size neutrals based on it. Keeping in mind, again, that neutral has to handle the unbalanced load between any phase conductors, and it's also has to meet the minimum requirements of 250-102C1. But the actual unbalanced load could be higher and require a larger size than what might be in 250-102C1. So that's why you have to compare the two and take whatever results in the larger. Also remembering that we can apply certain conditions. 220.61 would allow us to apply 100% to the first 200 amps. And then above that, we can apply a 70% to the remainder if those conditions apply. Okay, always keep that in mind. What's up, Mohammed? Thanks for coming. Robbie, thanks for coming. Estrada, thanks for coming. Okay, so now as we go, if you have some questions, feel free. Let's kind of not take it away from the topic. If it's an optional method, let's keep it optional. I know you people have pressing questions. You always know you can email me. And if you email me some questions, maybe one night we'll come in here and do a question and answer form, and I'll answer your questions. Because sometimes we need to look at them, because sometimes how you might type them on the screen is not really how you're trying to convey the message, and we want to make sure that we answer it as accurately as possible to the best of our ability. So tonight we're talking optional methods and all questions that relate to optionals. So we're keeping it at that. And after we do that, we'll maybe take a quick look at maybe some pull box for AWG and larger conductor pull box concepts. And then maybe we'll touch a little bit on transformers, give them a quick look-see, some of the basic transformer stuff, if we get that far, okay? It might not, because optionals can take up some time. All right, so let's see here. What's up, Nick? Thanks for coming. And for all you other people in the room that aren't saying, hey, because you're ghosting or you just don't want people to know you're here, shame on you, okay? Join the crowd, chime in, let us know you're here. Again, I don't mind you silent watchers. It's all good, but you know what? Chime in, join the group, okay? You think I won't like who you are? Don't worry about it. I'm not a hater on anybody. Come on in. What's up, DJ? Thanks for coming. Nick, thank you. All right. I don't know if y'all are ready. I'm ready. We'll kind of look at this. Now, I got the code book, and hopefully I've got all my bugs worked out. What's up, Vincent? Hopefully my audio sounds okay to everybody. If not, I'm sure Tim will let me know, because I'm going to rely on Tim to let me know. And hopefully it's not too muffled or overmodulated or whatnot, so that you can hear me. Again, it would suck if I went through all this and you literally could not hear me or did not understand what I was coming out, the words that are coming out of my mouth. So we want to make sure you get that. Again, I've been working very hard in the background trying to make the stream the best that it can be moving forward, so you can trust that I put a lot into it. Okay? And I'm not wearing my pretty blue shirt that Tim likes tonight. I'm gonna wear the orange one. Okay. You can tell orange is probably my favorite. Nick, I love you, man. Why would I not like you? I like everybody. Come on. I got no haters. Ain't no haters in the room. All right, so let's do get into some optional methods. And it might look very familiar because it is going to be the same basic. What's up, Wannafish? Welcome. It's going to be the same basic principles that we use in the one that I've done before online. Again, no need in recreating the wheel here. It's the basic same concepts. But we'll jump back and forth to the code book. Finally got that all sorted out. Back and forth a little bit so that we can kind of look at the code a little bit and understand it. Because tonight we're going to be working out of part 4 of Article 220. And so we're going to be dealing with the optional calculations and everything that's associated with that. What's up, Jay? Welcome to the stream. All right, so let's kind of get started. We'll look at the optional method here. And you guys will be able to see your chats, hopefully, on the left sides of the screen. It is small, hard to see, but it's the best I can do so you won't take up my screen. Okay? All right, so in this dwelling that we're going to be fictitiously working with, and again, if you have any questions, I can see them. So just make sure you can, if anything about what we're talking about, type them, and I'll do my best to address it, and we'll look it up in the code if necessary. So we're going to assume in this calculation that we're going to do today that the water heater, clothes dryer, any counter-mounted cooking units, if we have some in here, wall-mounted ovens, if we have some, and electric heat is all in kW, and it's going to be equivalent to kVA. Okay? We're always going to kind of assume that and kind of go with that premise that we're dealing with. Anything that you see kW, we want to make sure that we know that that's going to be equivalent to kVA, okay? And another thing is kind of just as a tip for exams or in general, always try for a calculation to resolve your value down into the VA. We want to get it to VA values so that we can calculate it. For example, 10 kVA is 10,000 VA. You know, we want to get it down to that 10,000. It's much better for us to work the calculation, okay? And I'm like you, I got my calculator here, just a basic standard calculator. Should all you need going into exams is nothing more than that. And most of the places, that's all they're going to let you have anyway, right? So we got our basic calculator in case we got to do any calcs, work this thing out. All right, so we've got that basic for it. Now, let's talk about this dwelling. So the dwelling we're dealing with is 35 by 55 feet. Okay, maybe it's 55 feet long, or however you want to look at it. 35 feet deep, 55 feet long. That's it. It does have a front porch. Now, that is included within the dimensions. So 35 by 55 includes a 7 by 10 porch. Okay, so it kind of told me this. The next thing we know is that we're going to have 4 small appliance branch circuits. Now, remember something as you go through exam prep and you learn stuff. The National Electrical Code requires a minimum of 2. But don't get fooled on an exam, whether it's standard or optional method, if they end up asking you about 4 small appliance branch circuits. That's okay. Just remember that each one of them are going to have a value of 1,500 VA each. So just don't lose sight of that, because it's a minimum of 2. But if you have more than 2, you have to account for it. So it'll be 1,500 VA each. So again, just a small tip. People on exams miss that all the time. So just kind of keep that in mind. And we'll look at that as we move through this. The laundry branch circuit in this house, which seems very odd that this is at 35 by 55 and it's got 2 laundry branch circuits. However, because that's what's given to us, that's what we got. So we got 2 laundry circuits. We got a water heater at 4.5 kW, or like I like to say, equivalent to VA would be 4,500 VA. So we got that. We got a dishwasher appliance there at 10 amps at 120 volts. We've got a waste disposer, an in-sink waste disposer. That is a 0.5 horsepower at 115 volts. So we already know we're going to have to go where? Back to 430. You guys that have been with me for a while, you know we're going to have to go back and we're going to have to try to find the FLC of that 0.5 horsepower based on 150 volts, 115 volts. You already know that. I'm sure y'all have seen this and y'all are very familiar with the routine. The next thing we have is a trash compactor, which I don't even know if they make these anymore, but I guess they do. I had one when I was younger. My mom had one. The thing stopped working about 2 years into it, so we just used it as a regular trash can. Kind of defeated the purpose, but well, I guess it was still a trash can. Anyway, we have a trash compactor, and that trash compactor is 7.5 amperes at 120 volts. So it actually gives us face value in amperes. So we know that we're going to have to convert some VA out of that. So we pretty much figured that out. Now we have 3 attic fans. I don't know how many times I've seen in calculations in classes when I taught the apprenticeship programs that people forgot about attic fans. And so in this case, there's 3 of them, and they're 4.2 amperes each. So in our values here, we're just giving them a total of 12.6 amperes. So that's just a cumulative of all of them. And also I should mention, the point of doing this tonight was not just to replicate something we've done. This is where we're going to go in and out of the code book. So this is going to be pretty challenging to go back and forth, and it's really going to put my software to the test. And so keep me updated on how things are going. So we've got that's your 3 attic fans. We've got a clothes dryer at 5.5 kW at 240 volts. Remembering, interesting enough, folks, you probably know by now that a clothes dryer is not a requirement of the NEC to be included in the home. But if it's there and it's in your calculation, then you have to account for it. Okay? But again, much like cooking, clothes dryers aren't a required circuit in the code. But if it's there, and most chances are it's there, you have to take that in consideration. Now, on an exam, not that I think they'll give you something this detailed, but again, if their question gives you a clothes dryer, then there you go. You have to calculate for the clothes dryer, and 220.54 is going to give us guidance on that, and we'll look at that too. All right, so that's 5.5 kW at 240 volts. We have a counter-mounted cooking unit, cooktop, at 7 kW. Okay. We have a wall-mounted oven, 6 kW. You and me know by now that we're going to probably treat that as a single range, maybe, or maybe not. We'll see how that works out. What's up, WW? Thanks for coming. Robbie, thanks for coming. I think I catched up with everybody. All right, so the next thing we're looking at is electric heat. Now, these are 3 banks of 5 kW each. We're going to take those at 15 kW, so that's going to become very important when we do our comparisons in 220.60, okay, that you all are probably well familiar with at this point. So we're going to look at all that and compare it. Now, we have an air handler, which is a blower motor at 3.2 amperes at 115 volts. Now, interesting stuff. I'm giving you tidbits stuff. That air handler's blower motor is going to be utilized for heat as well as air conditioning. So remember that, because we have to equate that for both the heat and the air conditioning when we're comparing the two. Okay? And then you've got the air conditioner compressor, which I always screw up when I'm doing. I was on some guy's show a week or two ago, and I just couldn't get it out of my mouth. I kept saying AC unit, but I was trying to say compressor. But it's the AC outside compressor unit. And what's up, Doug? Thanks for coming. Down in North Carolina. There you go, Tar Heel State. Whoop, whoop. I love North Carolina, by the way. Used to spend all of my every year in vacation at the Outer Banks, and I miss it being out here in Texas. We don't have any. I mean, the closest I can go is Galveston, and that ain't the same water as North Carolina. Trust me, it ain't the same. It just ain't the same. But at least I can get to there about 6 hours though. Northwestern. Let's see now. So let's see. Where was I at? Condenser fan motor. Okay, so that was, well, the air conditioner compressor was 16.6 amperes. Okay, y'all know how we're going to achieve that VA, amps times the volt. You know, we get it. All right, so and we'll do all that. Next is a condenser fan motor, which is all part of the air conditioning, and that is 2 amperes at 115 volts. Okay, so we pretty good. We kind of feel good about the lay of the land on what we're going on with these items, and we'll come back to it from time to time. Okay. Now, what does the code tell us that we have to do first? Okay. Is what should we do? So what we have to do now is go look and see Part B. We need to understand what we're doing in 220.82, the general lighting and general use receptacle loads, and see where we get started in this, okay, this application. So with that said, we're going to go to the code book real quick so we can give a quick look at it here. Everything works okay. All right, so I'm going to go to 220. And right when I say if everything goes good, it acts like it wants to stall on me. All right, so we go to 220. Bear with me as I scroll through my screens to get to the optional method right here. Okay, so we're at part 4, and we're dealing with the optional method. And it says in the general, it says the optional feeder or service load calculation shall be permitted in accordance with part 4. Now, when it says shall be permitted, basically what that's saying is that you use the standard method, which is part 3 of 220, but we're going to permit you to use the optional method. Now, the optional method is pretty much going to always result in a smaller service. Oh, wait a minute. I said I was going to add something on here, so give me a second. I don't want it to block the thing, but there you go. And I thought, foul language. Oh, yeah. That one I'm not removing. Because I don't want any foul language. You never know what their kids watching. Kids want to learn the code early on anyway, Bobby. So, is it Robbie? Robbie, did you use some vulgar language? All right. So, anyway. But I think I got rid of the spam thing, so you shouldn't see that thing spam stuff that y'all saw the other night. So I think I figured out how to do that. Okay. So anyway, you see on the screen, so in lieu of the standard method, I have no idea, Bobby. Just ignore them. I haven't turned that feature off, and it's hard to tell what they consider a dirty word. I'll be honest with you. I left that one ticked on there for some reason. I thought, well, maybe it'll keep people from dropping the F-bombs or whatnot, but I have no idea what. So just ignore it. So you can use, and you're the first one that's ever gotten that. So, take that as a badge of honor there, because I've never seen that one before. So 220.82 is going to permit me to be able to utilize this optional method. Okay, 220.80 tells me that. And then, of course, 220.82 is going to start me in the process and allow me to do that. Okay. Now, interesting thing about the optional method. Can't say poop. Was that a restricted word? Trust me, I didn't write that rule. All right, so here's the thing, folks. What it does is says this section applies to dwelling unit having a total connected load served by a single 120 through 120/240 volt or 208Y/120 volt set of 3-wire service or feeder conductors with an ampacity of 100 amps or greater. Okay. So one, we have to assume that it's 100 amps or greater. Now, typically, when somebody compares a standard to using the optional, if somebody does a calculation, okay, and they do it, one of the key factors is that it has to have an ampacity of 100 amps or greater. And that is a caveat to this application here. So it's got 100 amps or greater. It shall be permitted to calculate the feeder and service loads in accordance with this section instead of the method specified in Part 3 of this article. So that's what gives us the permission to use Option 4, or Part 4 optional method. It says the calculated load shall be a result of adding the loads from 220.82b, which we're going to go through, and C. It says feeder and service interconductors whose calculated load is determined by this optional calculation shall be permitted to have the neutral load determined by 220.61, which 220.61 falls under Part 3. So this is what, if you didn't know, this is what drives you to have to use the standard method in order to calculate out the neutral conductor. Okay? So there you go. So that was kind of a rundown of what gives us the rights to do what we're going to do, what the requirements are, and how we do them. Okay? Now, of all the calculations for dwellings, for example, this is the easiest one to do. So we should go through this pretty quickly, right? Okay. What is that question, Nick? I'm sorry, Lordy, I have to... Sorry, guys, it's hard for me to see it because I made it real small. I don't know how y'all could probably see it. I got a huge monitor, so again, sorry about that. All right, so there you go. So let's go on and get ourselves back to where we were here, right? All right, so here's where we're at. And the first thing, so Part B of 220.82, the general lighting and receptacle use load are listed as 3 VA per square foot area, very similar how we did in the standard. And of the outside dimensions of the dwelling unit, no differently than what we would do. So nothing we're going to do here is any different than what we did with the standard method starting out for the general lighting and general use receptacle application. Okay, it's just a little more straightforward with the optional method because it puts it all right there at the beginning. So in that scenario, if you look here in the code, it starts out with kind of saying, okay, here's B. It says the general calculated load shall be not less than 100% of the first 10,000 VA plus 40% of the remainder of the following loads. Okay, so we're going to work through each one of them, and you notice that the heat versus air conditioning and all the heat and air conditioning load it's separate in C. We're going to do everything that we would do typically in a standard method under B, and we're going to kind of condense it down. All right. So this is where it gives you the 3 VA. So if you wondered, that's where it's going to give you, and it tells you point blank that covers the general lighting and general use receptacle. When you look at how you do it in a standard, you got to deduce that, okay, and realize that in 220.14J, and you got to come to that realization that even though 220.12 says general lighting, that it also covers general use receptacles. So to be honest with you, in the optional method, it actually says things pretty darn clear, pretty quickly in the code rule, whereas the other one's kind of drawn out a little bit. Okay, so again, on an exam, you're probably going to get more standards, but I think you're going to get pieces of standard. But you do need to know the optional method as well, because again, I do know in some states they are starting to bring up optionals, and it's in the code, so it's fair game, okay, to do that. All right, so 3 VA per square foot. It also gives us and says the floor area for each floor shall be calculated from the outside dimensions of the dwelling unit. It says the calculated floor area shall not include open porches, garages, or unused or unfinished spaces that are not adaptable for future use. Great example of this would be, attics. If the attic is not adequate to support weight, it can't be, all of this is 2017, Estrada, 2017 code, okay? I don't do anything on here for 2020. All of that stuff's on Patreon, okay? Everything here is 2017. And that's the most adopted right now, so that's probably, primarily that. And that's what most people are going to be testing on right now, that kind of thing, okay? So in this scenario right here, and if you got questions, I'll catch up with the questions here in a minute. So again, we've got our floor area requirement, future use. An attic wouldn't be, even if I had stairs to the attic, to be honest with you, Robbie got 2 foul languages. Oh my God, Robbie, you're doing something, man. I don't know what it is, but you're doing something. What's up, Jay? Thanks for coming. It's hilarious. So just when I get rid of the other warning notice, hey, Terrell, just when I get rid of the other notice, what's up, Juan? Now I got a new notice I got to go hunting down, Robbie, because you're using some kind of foul language. Way to go, Robbie. Where's my Robbie one? Okay, so anyway, I get distracted easy, folks. All right, so in our case, unfinished, an attic or whatever, it's not adaptable for future use. Not going to count that space. Garages, not going to count that space. And then, of course, open porches. Okay, not going to count that space. All right, and of course, you see here on the screen, this is where we're getting the 1500 VA for the 20 amp small appliance and the laundry. Again, pretty straightforward, where in the standard method, you got to kind of hunt for this stuff. It's pretty straightforward right here. And then here's the part, before we look at a calculation, so I don't have to keep jumping back. Here's the part that I find the easiest thing to be able to do with an optional method. And we'll blow through these here quickly in a minute. Is the nameplate ratings. You literally gather up all the nameplate ratings. Now, I've had people tell me, Paul, I don't have all that information. I don't have all that information when I do a calculation. I'm sorry. I mean, I was able to do these calculations, and I was an electrical contractor in the field, owned my business for over 20 years. I did these calculations because I requested the information from the owner to get the information on what appliances were going to go in the dwelling. If you want to use the optional method, I have to know a nameplate rating. So again, I love to give you the scenarios of what ifs, but there's no what ifs here. You have to get the values. You have to know what it is in order to calculate, be able to do the service. So again, you're going to have to work with the owners. It just is what it is. And if you go with the if you don't, then your only option is to go standard method. And you go standard method, then you can take some base values and things like that. And when it comes to ranges, you either look for the value that it gives you, because you're going to need KW. With dryers, you can just go with 5. But again, if if the value of the dryer is higher than that, then it kind of screws you. So again, you're going to have to know these values. And so as an electrician, I just simply would reach out to the builder and say, I need to know all the appliances because I'm going to size this based on that. Or you end up oversizing it anyway and it becomes a moot point. But you have to ask somebody for this information. And I know people will tell me, Paul, it doesn't work that way. Yeah, it does. I've done some home. I've done quite a few homes in my career, so it does work that way. All right, so all appliances that are fastened in place, ranges, all that information, clothes dryer, you take everything at its nameplate value. Okay? And then item number 4 says the nameplate amperage or kVA ratings of all permanently connected motors that are not included in item 3. And of course, for our case, that would be like the attic fans and things like that. That would be a example of that, okay? And then you get to look at the heating versus air conditioning, and we'll look at that, okay? All right, let's kind of go back here. And let's see here if I have any. Let's see if I go back real quick to the main menu, and I'll see if I have any questions that I need to answer. Let's see here. Robbie says, will you ever have to assume voltage if it isn't given when trying to get the kW or demand factors? Robbie, you probably are going to know that it's a 120 to 40 volt service. So you can use those values. Those are nominals. And for example, when we look for the sample example in motors, now if you have any motors, then it does tell you at the beginning of 430 over those tables that, again, that if it's a 120 and the motor size is given as 115, then you use the 115. Okay, if it's 230 motor and you have a 240 volt voltage, you're going to use the 230. Okay, so again, that's kind of the guidance that you'll get on that, which you would have to do anyway because the motors don't come in the same brand circuit, sizing, the nominal voltages. They come in their motor voltages. So yeah, you would have to do that. As far as guessing for motors or something that or some appliance, the values, I never guess. I need those values, and the contractor, general contractor, somebody's got to supply them to me to be able to do that. Now, of course, I will not lie. I will say, as a contractor, and when I was doing projects and we were doing a lot of the same projects, I could look at it and tell you what that service needed to be for that building. And I think it doesn't become brain surgery for us because we look at it and go, that's a 200 amp, that's a 400 amp. That type of thing. Where it gets kind of difficult is when people are looking at 100 amp or 150s or 175s or that type of thing. Although a 200 can handle 175 or even 150, most certainly can handle 100. So I think most people are error on that. But what we're talking about is a little different than the real life, sadly, because in real life, we've got those variables. On an exam, this might answer your question, Robbie, even better. You never guess on an exam. If they don't give you the values, that's just a poor question. And not to say that there's not poor questions out there, because there are. We've seen a couple in the last week or two, right? But the reality is they have to give you the values. So the good thing about an exam prep is that they have to give you the values that you're working with. There's no assumptions. And if there is an assumption in the test center, do me a favor. When you leave that test center, quickly as you can, hey Juan, thanks for coming. Hey Terrell, thanks for coming. Hey Jay, make sure that you, quick as possible, y'all guys do me a favor. Write it down on paper. Keep a notepad right there in your car when you get out of your testing while it's fresh in your mind. Write things down because I will fight that state for you. I will get involved in it, but you got to be accurate with the question. I know it's hard because we get so wrapped up in the questions to remember what to write down, but do the best you can, because if a test question gives you really crappy data, how can you give them an answer? And so you should be contesting any question that gives you crappy data. But contact me and I'll tell you if it's crappy data that's poorly written, and then you can go after it. And you know what? You might have them turn a question around in your favor. Okay? So again, just some things to think about. All right, let's get back where we were. All right, y'all ready? All right, so in this case here, We knew that it was 35 by 55, and of course we had that 7 foot by 10 foot, right? What's up, Ken? Thanks for coming. So again, we did 35 by 55 is 1,925 square feet. Now, of course, we said that the porches don't count, and that was included, so we have to take that out. Okay, very sneaky exam type of question, where it tells you it's included, gives you an overall value, and people forget to take it out. So in this case, 10 by 7 is 70. So we want a 1925. We take that 70 away. And that is 1855. And if it's math, you can double check my math. Tim, if I got any wrong, forgive me. Again, I like to do my calculations while drinking. So in this case, 1855 times 3 VA, which was afforded to us by 220.82, remember? That is 5,565 VA. That's the first thing you write down. And remember, that's your general lighting and that's your general use receptacle loads right there. 5565. Write it down. Okay? All right. Next. I can get to my slide here. Okay. Next. All right. We're looking back in here. So we've pretty much accomplished this right here. Right? Next thing is this small appliances. No biggie. So small appliances, branch circuits must be included when calculating a dwelling unit service per 220.52a. Okay, we got that. Each small appliance branch circuit is calculated at no less than 1,500 VA. A dwelling unit must have at least 2 small appliance branch circuits per 210.11c1. All this stuff we're familiar with. So we got 4 of them in this dwelling. And if you're on an exam and you're doing a question, they're going to give you the number of small appliance branch circuits. Now, when you ask, for example, about assumptions, if they want you to do an overall calculation, you do know that the code requires a minimum of 2. Okay? So if they ask you for the calculated load of a dwelling unit, and they know that, and you know that you've got to do the square footage, the 3 VA per square foot, then you automatically need to assume 2 small appliance branch circuits in 1 laundry circuit at 1,500. Okay? Not the 4, the 2 that are at least required by code. Okay? All right. Now, if they ask you just to give you the general lighting and general use receptacle loads for the dwelling, then that's all you're doing is giving them what we just did a second ago. That's it. Don't go too deep in it. All right? So in this case, we previously looked that it was 1,500 VA each. There's 4 of them. So 4 times 1,500 is 6,000 VA. That's the second number that you write down. Okay? The third one is we looked at was the laundry. Now remember 220.52b says that we have to have the laundry circuit calculated in the dwelling load. And we have to have at least 1. But in our case, we've got 2. So we need to account for both of them. And we do this no differently than we did the standard method. It's no different. So it would be 2 times 1,500 VA, so that's 3,000. So that's your third value that you write down. Okay? Now, we have the general lighting receptacle, we have the small appliance branch circuit, and we have the laundry loads together so that we can apply some demand factors based on known diversity. Okay? And diversification. Well, that sounds even fancier, doesn't it? Diversification. All right? So now, let's come back to me. Okay. Now, we're at this stage. We went through the top 3. What do we do differently? So, as you can see on the screen, it says, now we're here. We began to do things differently than we previously did in the standard method. So, up to this point, we didn't do anything different than the standard method. So, if you learn those 2 ways to pull that information together, it's going to serve you very well. Just remember now, if I'm doing an optional method and I got to do a neutral calculation, that the values that we did just now are going to be exactly the same as you would do in a standard method. So if you are doing an optional method, now you got to go do the standard method in order to size a neutral. Remember, you've already done half the battle when it comes to the first one, because every load you see here is going to be a 120 volt load. So it's going to have a neutral component. Okay. So you're going to count these loads in the neutral calculation as well. Okay. So again, whatever saves you some some time, that type of thing. Okay. All right. So the A part is simply setting up the parameters to use in the optional method, and the ampacity has to be 100 amps or greater. We established that. Okay. But at this point, we haven't done a whole lot of different stuff. Okay. Again, we're going to remind you, you got to use the standard calculation for neutral. So far, we haven't done a whole lot different. Would you agree? I think you would agree. All right. All right, so now what we want to do is we want to add all these up together. So this is 5,565. That was the first thing we did. We have 6,000 was the second we did for the small appliances, brand circuits. Third was 3,000. That's 14,565. Now, unlike how we did in the standard method, okay, we want to take these numbers and keep them aside. Okay, because now we have to continue on with the appliances. But this is a number we want to keep. 14,565 VA. That took care of our general lighting receptacle load. So if you are on an exam and they want to know the general lighting and receptacle load for the optional method, and this is all they're asking you for, when they ask you maybe what is the connected load versus the calculated load, then this is the stuff that we're looking at here. This is the pure values, okay, that are required in VA. This is the pure value of it. The calculated load would be after we apply some type of demands to this. The connected load is purely as we see it, okay, right here. All right, so write that number, 14,565, write that down somewhere. Okay, we're back to our list, so we're going to knock this out. So now we can work on these appliances. All right. The term appliance designates utilization equipment commonly built in standard types and sizes and is installed as a unit to perform specific functions. Water heaters, standardization, dishwashers, disposals. All of these, you buy them, they're very similar. Variations on manufacturers' creativity is expected. But again, those are utilization equipment. And when you see that term utilization equipment in the code, remember that utilization equipment is very broad, and appliances that are very specific are, lucky for us, those that we deal in mainly with dwelling applications are listed pretty good in Article 422. Okay? But there could be other pieces of electrical equipment that are considered utilization equipment that connect to an outlet, okay? Whether it's, hardwired or whatnot, right, to an outlet. And remember, we're not talking receptacle outlet. We're talking outlet, a point where we take power from the system, okay? So anyway, let's don't get too deep on that yet. All right, so the purpose of this load calculation, a kW rating will be the same as kVA, so we've already established that, okay? Now, we're going to venture into appliances now. So remember, we have to take that hat and get it ready, because now we need horsepower ratings on these motors, and we have to convert it to VA before we can even utilize it in any of our calculations. So I tell people this little tip on exams, okay? Here's what I tell people. What I tell them is you need to make sure that when you get an exam question and they're asking you a bunch of motor questions and you see a horsepower, the first thing that you need to do, guys, is to go to 430, tables 248, 249, and 250, depending on what you're dealing with, single phase, three phase, or whatnot. And you need to find the FLC. You need to find that FLC, okay, based on the horsepower. Because then we need to convert this over to VA so we can continue on. But I tell people on the exam, do that right away. So when you get a calculation question, guys, and you're in an exam and it's a motor question or whatever it might be, if it's given to you in horsepower, immediately stop, drop, and roll over to 430.248, 249, or 250, depending on the single phase, three phase, or whatever you're dealing with. Okay, that's the first thing. All right. So that's it. That's the important part, okay? Just remember those things. I don't want you getting so involved in a question only to spend 2 minutes, 3 minutes on it, right? And then notice that your motor is an 8 horsepower and you need to convert it. Now you're going to take extra time. I prefer you to see that, let that be a trigger, head your butt over and get the FLC, and then come back and do your calc. That's just a mental training to save you time on an exam, okay? That's all about time, okay? All right, so one good thing to remember, once we do all that, one good thing to remember is that when we're dealing with appliances, okay, you get a benefit, okay, in the standard method, but you don't get it in the optional method. And that is when you have 4 or more appliances, I get to apply a demand factor of 75% reduction. I don't get to do that with the optional. And you might say, well, man, then what makes optional a benefit? Well, remember, you're getting to take the first 10,000 at 100% and then the remainder at 40%. I mean, that's a huge discount. So you're getting ready to you're able to do it in a bulk, if you will. Okay? A bulk. So again, always going to result in a smaller service with the optional method. Okay? All right. A tip. Multiply the voltage by the amperage to produce the VA. So remember, volts times amps equals VA for calculation purposes. Kind of ingrain that. Okay? All right, let's go on. All right, as you can see here on the top of the screen, here are our appliances. So we got the 4.5 kW. We know, you and me know to convert that. So it's 4,500 kW, which results in 4,500 VA. We have a dishwasher. This was 10 amperes. So what did we say earlier? 10 times 120 is 1,200 VA. Okay, easy conversion, quickly. Horsepower. Well, in this case, we have a half horsepower, so we're going to go where? Immediately to table 430.248, and we're going to go into the column. And, of course, we know that it's a 115, so we're going to go to 115 column, come down, and you're going to see that that is what? 9.8 amperes. So that's what I was saying. Go on and convert your motors first, quickly, when they give you HP, horsepower, okay? So, again, 9.8 amps times 115 volts. And, oh, here's the thing. Use the values that they give you in the question. Don't go, well, Paul, it says 115. I know I pulled a motor that's 115, but aren't we supposed to use 120? No, use what they give you on the exam. Okay, use the values they provide for you. The next one would be the trash compactor. 7.5 amperes times 120 volts is 900 VA. And then, of course, the last one we have is our 3 attic fans. And these 3 attic fans are, again, covered under Note 4. They're not necessarily appliances, but they are the other motors, and we have to account for them, right? So in this case, it's 4.2 amperes each times 3 is 12.6. We already were given that. And do 12.6 times 120 volts. And that's 1,512 VA. Now, it's just a simple process of adding them all up. So we have 4,500, 1,200, 1,127, 900, and 1,512. That is 9,239. Okay? Now, if you look at it, we also include ranges, wall mounts oven, counter mounted units, and water heaters as well at their nameplates. However, it's important that we pull those values directly from their nameplate. Okay? And of course, with the water heater, we have it. We already have the established value that was given to us. Okay? So let's go. So we've got our values here. For these are the fixed in place appliances that we're covering. Okay, now we're going to move into the other aspects of it. So we have that clothes dryer we got to deal with. So you take that 9,239 we had, keep that, write that down, keep that in your little package there. Now let's tackle that clothes dryer. Now the clothes dryer is not a requirement of the code for load calculation. If there's not one in your calculation in your exam question, then don't assume one. Skip it. But if it's included in there, you have to account for it, okay? You can't ignore it. If it's in there, it's in there. So in this case, this clothes dryer was 5.5 kW, okay? Now, It says in 220.82b3 to take the dryer nameplate when using the optional method, so we take the full 5.5. Okay, not like what we did with the standard method. Okay, here we're just simply taking the nameplate. That's it. And again, we want to convert it. Pretty simple to convert. So 5.5 kW equates to 5,500 VA. Break it down into VA. It's just going to make your life a lot easier to get used to that, to kind of get it in a rhythm. Now, remember all these loads here? Notice that except for the water heater, all of these loads are neutral loads. So there's going to have a neutral involved in it. So while you're doing this, I always kind of keep track. For me, I always put a little mark beside it to let me know that, hey, these are all neutral loads. Okay, these are all dealing things that are going to require neutral calculations. But remembering in my mind, I still got to go do the standard method. But some of this calculations that you do is not going to change. Okay, whether it's optional, it's 7.5 amperes times 120 to get a VA. That's not going to change whether it's optional or standard. So you've already done half the work. So you might as well put a little mark there so you don't have to redo it again. And usually I put a little mark, even if it's on a test and sort of dry erase board, you just make a little mark and put an N beside it for neutral. That way you know if you happen to have that kind of question on an exam. And some tests are pretty, might have something like that. Just keep it in mind. All right, so again, so in this case, there is no, there is a neutral for the clothes dryer, right? Lucky for us that we can use 220.61, which is 70% of this value. So 70% of 5.500 is what we'd utilize for the neutral load, okay? But again, that's using the standard method. I'm just kind of throwing you a little reminder out there that this is one of those you'd put a little mark beside because there is going to be a neutral load associated with this clothes dryer for later on. You with me? All right, so we can carry over the 6,929 from the normal fasten in place, permanently connected. Actually, I think that is actually 9,239. Not sure where that came from. There you go. I said somebody needed to check my slide there. All right, I fix it right here. Here's where it's fixed. Okay, you bring it, and now you add that 5,500 VA to it. So that is 14,739. But we're not done yet. Okay, we carry over that 14,739. Now we have to tackle the cooking. Now, before we tackle the cooking, I want to come back and see if I have any questions before we tackle the cooking, because then we're almost done. Standard says 4 or more appliances. There are 75 demand. I think this isn't a standard method. This is the optional method. You can do that in the standard method, but you can't do that in the optional method. Optional method, full nameplate. And that's what we're doing tonight. We're doing optional method. Okay? All right, and it says, so laundry circuit is not required in the optional method? Okay, so I'm thinking, Robbie, that you came in late. For some reason, because I'm going to go back here and show you. Here's the 2 laundry that we did. 1,500 VA each. Okay. Right here. Okay, so I'm gonna assume you came in late and just totally blanked out on me on that one. All right? Okay. No, Robbie, we're not going to talk 210.23a exception. We're doing optional method tonight. If you want to talk about it, we'll do it after. Don't bogard my stream, all right? Okay, so again, in this case here, we're going to look at the cooking, counter-mounted cooking and the wall-mounted oven. So the household cooking appliances, range, wall-mounted oven, counter-mounted, blah, blah, are not required in a load calculation. They're not required. Believe it or not, you're not required to have cooking circuits in your house. But we know they're all there in order to qualify as a dwelling. You have cooking, cleaning, sanitation, and living. What house is not going to have cooking? So again, but I'm just saying, if you get an exam question that doesn't show cooking, you don't assume cooking. Because you can't assume something they don't give you, right? All right, so another thing to remember, if there's no cooking appliances rated over 1.3 kW, then no need to add any calculation. You just take that value. You only have to do demands or other calculations when you're over 1 3/4 kW. Okay? And that's where we get into 220.55. Okay? So in the optional method, we keep it simple. You simply take the nameplate of the cooking equipment. Remembering that, again, we can apply the 70%, okay, to these values when we're sizing the neutral later on, when we're doing the standard method approach to it. Okay? All right, so the counter-mounted is 7 kW, so that's 7,000 VA. Remember, we want to convert to VA. And we've got the wall-mounted oven, which is 6,000 VA. So we want that value right there. They convert pretty easily. So you guessed it. We take the 12,429 from the previous slide, in which, again, I have no idea where that came from. So basically, we're going to take the 14,730. Oh, I know why. Sorry, guys. This was another presentation that I did, and I left it in there. My bag. So we're taking the 14,739, which is what we got here, plus this 7,000, plus this 6,000. Ignore this right here because that's from another thing that I was doing, and I changed it. All right, that gives me 27,739 VA. Okay, so the value for our cooking was 13, which is a total of 7 and 6. Okay. All right. So with that said, so you see the values here, everything that we've got. Now, let's take the general lighting, which again was 14. So now here's what we're going to do now. Now that we've got all the appliance, we've done everything that we need to do in Part B, right? We've done everything in there. We've done our general lighting, our receptacle, our small appliance, our laundry. We did our fastened in place. Okay, we did our cooking. We pulled everything together, right? Now we get to do what it says for us to do at the beginning of Part B of 220.82, right? So here's what we do. So we had 27,739, okay? And we had the 14,565 from that first set of steps that we did. You add them together, that's 42,304, assuming my math is right. First 10,000 VA at 100%. And the remainder at 40%. So I like to take the 42,304. I like to take the 10,000 away from it so I know what to apply my 40% to. It's just much easier for me. So I'm taking that 10,000 away. So that's 32,304 VA times 40% or 0.40 equals 12,921.6, or using 0.5 rounding, it becomes 12,922. Then I'm adding back in that 10,000 that I pulled out, that has to be at 100%. And that gives me 22,922 VA. But we're not done. That's just a point that gets us to gets us up to Part C, okay? But I need to remember that number, okay? So that's the total for the Part B of 220.82, okay? Now, let's take a deep breath and let's look at what we're doing here. We're going to tackle the heat and air conditioning. Unlike the standard method, when you compare in the option method, you have size options and you simply choose the largest of the options that apply. Okay, so first things first, we have to convert those values in VA as I've talked to you from the beginning. Anytime that I see something, I need to convert because I'm working in VA. I need VA. Luckily for us here, they didn't give us anything in horsepower. They gave us the amps. So rather than try to go hunt something in 430, nope. We're going to use what they give us on the exam, what they give us in the question. Okay. So in this case, check my math, Tim, is 16.6 amperes times 230, because that's what they give us, is 3,818 VA. The condenser fan motor was at 2 amps. Times 150 volts, which is 230 VA, okay? And that air handler is at 368, okay? Which, again, in us calculating the air handler was right here, which was 3.2 amps times 115 volts, okay? And I say as again, so I don't know where I did it. I must have done it somewhere else. Can't remember where I calculated. But anyway, that's what it is, 368 VA. Okay. All right, and of course, the heat is 3 banks of 5 kW. So that's 15 kW. Okay. Now that we know the VA, we've calculated out, we've written these all down, we can now see what systems we actually have. All right. So what does it say? 220.82C1 says 100% of the nameplate ratings of the air conditioning and cooling. Well, we do have air conditioning in our values, so let's look at that. So the air conditioning is 16.6 amperes times 230. That was the 3,818, and that's what we had before. The condensing fan is 230. That's what we had before. And lastly, the air handler was 368. That's what we had before. That's 4,416 VA. So 100% of the AC is 4,416 VA. And that is what 220.82C1 is asking. So write that down. Put that little bad boy down on paper because that's your AC. Okay. Next. 220.82C2 says, NEC says 100% of the nameplate ratings of heat pumps when the heat pump is used without any supplemental electric heat. Well, since we just did 220.82C1, so nothing additional is added. However, if you have a heat pump and they give you the nameplate value, take that at 100% and compare it to everything else. Okay? Wasn't our case with ours. Nothing was stated otherwise for that. Okay? Next one was, I'm just kind of giving you all of them in the list, okay? We did the AC. So far, nothing else applies to us. 220.82C3 says 100% of the nameplate ratings of the heat pump compressor and 65% of the supplemental electric heat for a central electric space heating systems. If the heat pump compressor is prevented from operating at the same time as the supplemental heat, it does not need to be added to the supplemental heat for the total central space heating load. So basically you have to just take the heat loads at 65% and that's it. If it prevents the AC from coming on when the heat comes on. Okay, that's supplemental heat. Okay, so that's not our case, but we haven't been given anything otherwise in our calculation, so we're not going to assume that. The next one on your options list there in the optional method, and I'll show you that on the code here in a second, and I'll show you what we just went over. 220.82C4 says, well, how about 65% of the nameplate ratings of the electric space heating if less than 4 separately controlled units? Okay. Well, in this calculation here, we're going to assume, and we have to assume, on an exam, they're probably going to be very definitive, whether they tell you it's a heat pump, whether they tell you it's baseboard heat, or whatever they try to tell you it is. They're going to be pretty definitive. Okay. So for the lesson here that we're going to do today, we're just going to kind of use a couple examples that I just want to make you aware of if you get into this scenario. If it's baseboard heat, for example, they're probably going to be separately controlled. They're not going to have any blower. So again, I'm not going to worry about any blower motor or anything like that. I'm not worrying about any of that. I'm just looking at the heat separately if it's baseboard heat. And that's what we're going to go on the assumption here with this, because we don't know any otherwise. And I didn't write the question, so we're going to utilize that. So in our case here, but just remember, it's not difficult. It's just look at what they're giving you on the exam so that you can pick C1, 2, 3, or 4, whatever is pertinent to the question. And just follow what it says. You already have the values. They're right there. Just follow what they ask you. So in this case, we have 3 of them at 5 kW each, along with the air handler blower motor. Never forget the blower motor. So in this case right here, we're going to assume for our calculation, we're going to assume that we have the blower motor and it in some way moves this electric heat. Now, look, between me and you, to be honest with you, I have had this problem with the person that wrote this because they don't make it real clear. Because typically if I had baseboard heat, it ain't got a thing to do with the blower motor. So my point being is that however it happens, whether you use the 368 VA for the blower motor or not, it's not going to really affect your calculation. But in our case, we're going to show it two ways. I'm going to use it in a situation like here where it's used as electric space heating. And because I don't know any different, I'm going to add the blower motor in. Okay, but you could be very much justified if you were to say this is baseboard heating and you took it off. And also, somebody could argue that this is a heat pump. Okay, but I wasn't given that in the question, neither were you. So we're going to treat them as such. So I'm working for worst case scenario. All right. So in this case, and incidentally, it wouldn't matter because even if I took the 368 away, the 1500 VA is still going to be dominant. It's going to be the dominant value of all of these. Remember, the AC was only 4,000 anyway. So again, you pick the one that results in the largest value. Anyway, I'm trying to give you all scenarios here. All right, so again, so this would be 15,000 VA or 15,368 if we include that blower motor, if it blows the heat around. Okay, so in this case, we take the 15,368. I'm going to apply the 65%. Now, why am I applying this? Remember what I said? I'm going to give you all the different scenarios. So I'm trying to give you all of them. If it was, in our case, I'm going to apply the 65% because I'm going to treat these as electric space heating. Okay? And it's less than 4. So I apply this value at 15,368 at 65%. And that results at 9,989. Now, incidentally, just for craps and giggles, it was 15,000 times 0.65 anyway. So it would be 9,755 anyway if I didn't count the blower motor, if that wasn't intended to be part of my calculation. Okay? Read your questions. Okay? Mine are very broad, but read your questions in depth. Okay? So far, it looks like this is the winner. But we have 2 more to cover as a lesson. But in real life, based on the above equipment, we would actually be done now with 220.82c. This is the value that we would add to our calculation. But we have 2 more to look at. This one says if it used 40% of the nameplate of electric space heating where there's 4 or more. So if I had 4 or more banks or baseboard heating or whatnot, then I could apply 40% to the nameplate overall. Okay, well now, we have 3 of them, we have 4 of them. So again, we would not utilize the 40% because we have 3, okay? But just remember, if you got 4 or more, this would be something you have to remember. And of course, the last one is C6, and that is 100% of the nameplate rating of electric thermal storage and other heating systems where the usual load is expected to be continuous at the full nameplate value. Then you would simply take that full nameplate value. Okay? Systems qualifying under this section shall not be calculated under any other section in 220.82c. So I can't use C1, 2, 3, 4, or 5. I would only have to pull that value if I utilize this, okay, and it's expected to work continuously at its full nameplate value, continuously being what? Continuous. Then I would use this one, but I can't cherry pick C1, 2, 3, and 4. I would have to choose this, okay? And then I just would keep it at what? 100% of that nameplate value, and I add that to my calculation. Clearly, this one doesn't apply to our one-family dwelling, so we wouldn't utilize it. So we verify everything that we've done here. Now, what I'm going to do real quickly is go back here and stick with me, Robbie, because we will get there, because I'm not going to forget you when we get to our Q&A. So you've got all of these things here, and I think we touched them all. I think we did them all. Okay, so we're good to go. So let's take all of the values that we previously did. From B, there was 22,922. Then what we just did in C was 9,989. We add them together, and that is 32,911 if my math is worth anything. Now, in order to find the conductor size that we need, and to verify that we're at least 100 amps or more to even be able to do this in the first place, remember that requirement? Okay, we didn't lose sight of it, is 32,911 divided by 240. That's 137.12 amperes, or 137. We can drop the 0.12. and it's 137 amperes. Okay? And what allows us to drop it? The statement in 220.5b is what tells me. Now, since that statement is in 220, it applies to all calculations within 220. Okay? In the scheme of life, real world, a couple points, a couple VA, a couple hundred VA here or there, it's not going to really change too much. Okay? In an exam, I doubt they're going to give you all these things, but just be ready to take them all in pieces. Okay? All right. Now, with that said, we needed one for 137 amperes. What will we do once we have that value? The first thing that we need to do is go to 240.6a and determine what our amperage rating is on our device. And we see that since it's 137, we're going to need a 150. Okay, so that's the rating of our service for that application, the rating right there. All right, now, this is the thing that tends to happen. Now, let me come back to me real quick, because this is something that we want to talk about real quick. Well, the C6 has to do with a thermal energy heating system, Bobby, where it goes down. It's first of all, it's going to be labeled as a thermal heating type of system, and it's going to be labeled as something that's going to pull its current at its full value continuously when in operation. Okay, it's not like a normal heating system or normal HVAC system that's going to go on and off. Okay, it works at a constant rate, and it's supposed to keep a temperature at a constant value, and you will know it. Okay, and since this is exam prep and not theory life, you're going to know it on an exam because they would have to tell you that it's thermal. Okay, they would have to tell you that. So don't overly try to get into the theoretical concepts tonight, okay? Just understand what you got to do for an exam. And again, we'll have training as I move forward on different things like transformers and theory and if you want it, hysteresis, losses, and all that kind of theory stuff. But don't let that get in your head if you're here to prepare for an exam. Don't do it. Nothing will happen but get rattling around up there and screw you over. Just take it at what it says in the code, okay? Don't let it screw you. You move me a little bit, okay? All right. So in this case right here, it's important. And here's what happens. On an exam, you always want to, many people will look at the 150 and then will immediately go to 310-15B16 and size that accordingly. In reality, if the service falls between 100 and 400 amperes, and we're dealing with a system that is going to be a one-family dwelling, for example, and it's going to allow us, and it falls within the parameters of 310-15B7, then I'm going to be able to utilize the table 310-15B7 for my conductor size. Now, the rating of the service stays the same. It's 150 amps. You need to actually know that rating to be able to apply 310-15B7. You have to know that rating. So we base that on 240.6a, and that's what we get the 150. Now, here's the thing. If I utilize that little table, which incidentally comes back into the 2020 code in case y'all didn't know it, it's coming back. In the 2017, it's based on 83%, and the table is still there, I think, but it's up in the informative Annex D. I think it's still there. But reality is, I liked it better when we just did the 83%. I can't stand that table, to be honest with you. People love that little table, but I can't stand it. Because it makes people think that that's the ampacity, no matter what, that I can use it. Luckily, we added a note in the 2020 that says, oh, by the way, if you've got adjustment or corrections to do because of ambient temperatures or the number of conductors that exceed 3, oh, by the way, you can't use this little table. But in our case right here, this is 2017. We can use that table. We use the 83% rule, but we can only do that again if it is not more than 3 current carrying conductors and there's no adjustments or corrections. I know, Jay, you told me you love that table. But Jay, I think I remember you a couple phrases ago here says, hey, Paul, I love calculations. If you love calculations, then you got to not like tables because the 83% was a calculation, bruh. That's a calculation. You got to love that. Forget that table. 83% is all we need to know. Okay, anyway. So anyway, so again, in our case, it was 137. We have a 150 amp rated device. That's a service rating of 150 amperes. Beautiful. We can apply 31015B7. Okay, so what do? How do we do this? Well, we take that 150 amperes, okay, and we're going to apply the 83% to this to do it, okay? So what are we going to do? I've got my calculator. You have yours. We take 150 times 0.83, and that equals 124.5. Or 0.5, we're going to be 125. Okay? I'm getting relaxed now, man. I'm laying back in a chair, pulling the mic to me instead of leaning forward. I am just chilling out. All right, so that is my value, right? 124.5, which we're going to make 125. Then we select conductor from the 75 degree C column in 31015B7, which will be a 1 gauge, which is good for 130 amperes. So this is the minimum size conductor acceptable if all the rules in 31015B7 are followed. Now somebody's going to ask me, why can't I use the 90? Remember, we would do that for adjustment and corrections. In this case, our terminals are rated at 75 degrees C. Most of them are. There's none that are going to be rated at 90 in that equipment. Okay? So you're going to use 75 degrees C. Now be careful on an exam that they give you something that says consider the terminals at 60 degree. Or be careful. In this case, most all services are going to be over 100, so 110.14c is not going to be into play too much. But I just want you to be very, I'm going to use a big word. You ready? I want you to be very cognitive. Cognitive. Jay, I'm probably saying that wrong. But what I mean is I want you to be very aware of what's in the question. And I have to remind my guys in the Fast Tracks program all the time, slow down and read the question. Oh, where's my mask? Hold on. There's always one person out there, okay? There's always one out there. Robbie's that guy tonight. That's for you. That's for you, Robbie. I'm practicing social distancing in my own freaking house, bro. And now my glasses are fogging up. Oh my God. Can I file a lawsuit against the state if I put this on my face and I'm going down the road and my glasses fog up and I die? And the guy goes, Paul, why were you wearing it in the car? Dude, you're intelligent. All right, I got to take that off. Sorry. Ooh, that thing's nasty. All right, anyway, enough of that. See how I get sidetracked so quickly? All right, usually it's Danny that does that, but I don't know what happened to Danny. I hope he's okay. I haven't seen him in a while. He hasn't come in here in a while. I'm better looking. Yes, I was better looking. Except for the fact that it says the Dallas Cowboys for all my Dallas Cowboy haters out there. I'm not a football fan, so. But anyway, it was given to me. My son gave it to me. Okay, so where are we at? All right, so let's get back to where we were. So we did it at 125, and now we have to find a conductor that's good for 130 amps. Well, that was what 1 gauge was, right? So this is the minimum size conductor acceptable if we apply all the rules. Now, that's copper. And we're looking at, if it was aluminum, what would we do? Well, if it's aluminum, your conductors of choice, 75 degree column, go to the 31015B16. The ampacity is 2-aught aluminum. It's good for 135 amps, which will work just fine as well. Okay? Works no problem. Okay, bonus question. I don't have a button for that, but yeah, I do. Here you go. Let's see you guys that are doing exam prep. What is the minimum size of grounding electrode conductor to a water pipe grounding electrode? Assume that it's been supplemented already and we're not worried about that. What size would you require to the water pipe ground? Water pipe ground. Okay. And we did this base, and I'll tell you, we're going to use the 1 gauge. We're going to use the 1 gauge copper. You know, some people ask me, obviously I work for a manufacturer that makes copper and aluminum, and for the longest time, people had such a freak out about aluminum, and I just didn't get it. Now, back in the late 60s and early 70s, it was 1350 aluminum. It wasn't even the big deal, but people freaked out about it for some reason, and it was the terminations that were the problem, not so much the aluminum. But now everything's 8000 series. It comes in a building. The code requires that. So in that case, that's just as ductile and flexible as copper is, to be honest with you. All right, so we know it's 1 gauge, right? Let's go to the code. All my code warriors here. So we're going to go to 250.66, right? Let me scroll through this. Geesh, I went really too far really quickly, didn't I? Some of y'all might say I'm getting more savvy in my PDF usage. Okay, so we have a 1 copper, 6. Wow. Let's see what we got. 6. Everybody got 6. Ooh, the sign of the demon. Not good. Should have picked another size. All right. So what size is it if it was aluminum? Four. That's right. No, Tim, it wouldn't be 250.66A. We're not using the allowances in A. Shame on you. 250.66A is for connections to rod, pipe, and plates. We're using the base 250.66, which sends us to table 250.66. Okay. So, interesting. Now, before we go back to the presentation, let me say something about this. Interesting, a topic you should bring up, kind of indirectly, Jay, is if I have a 2,000 amp service, I could have 5 sets, 6 sets. I could have 6, 7, or 8 sets of conductors, right? And it doesn't really matter if I had a ground rod. It doesn't have to be larger than 6. It could be a 10,000 amp service. Only requires 6 gauge to a ground rod, pipe, or plate, because that's all they can handle anyway. Okay. So, I mean, at the end of the day, of course, they got to be supplemented themselves. You know, got to have 2 unless you can show that it was 25 ohms or less. Then you can result back to 1, for example, for ground rods. But other than that, doesn't really matter, you know, when it comes to the ampacities, when it uses A, B, and C. Doesn't matter. Those are minimum size requirements there. Could it be larger to ground rods? Could I run a 4/0 to a ground rod? Sure. I don't know how you connect it. You probably have to CAD weld it. And I have engineers who do this stuff all the time, tell you to run a 4/0. What they don't realize is that's like putting 10 pounds of crap in a 5-pound bag. It doesn't matter if I run a 500 kc mill to a ground rod. The ground rod can only handle so much anyway. So again, that's just wasted copper. It's just wasted aluminum. But since I sell it, feel free to keep wasting it if you like. I'm just saying. All right, so let's get back to real quick to our optional. Okay, so we established everything good here. Now, let's look at what we're doing for neutral. Now, in this calculation, the values don't change, but you'll notice that all of these in green up here utilize a neutral. All of these right here utilize a neutral. This one utilizes a neutral, and this one utilizes a neutral. Everything else is 240, whatnot. It's not going to utilize a neutral. However, the dryer and the cooking units do utilize a neutral at 70%, right? Okay, so that's what we're establishing it. So this one becomes easy. Now, when we say you got to use the standard method, there's a misnomer here. The values that we're pulling together, we're still going to use the principles of the standard method, but we can still use values that we came up with, okay? We can still pull things together. So in this case, we still have the calculation that we did, 7,048. Then we come down here and pull all of our appliances. You see we already did this math before. Nothing changes, right? So we got 1, 2, 3, 4, we got 4 of them. So here's where the difference kicks in, folks. The beauty of it. Now that we're going to use the principles of the standard method, guess what? We get to kick in that 4 or more to 75% application, all right? So in this case, we can apply the demands. And yes, the demands do get to apply to the neutral as well, okay? What's good for the goose is good for the gander. If it's a VA that's good for the ungrounded conductors, it ought to be good enough for the neutrals, right? Because it's going to see the same value, theoretically, right? Okay. So in this case, we take the whole value and then we do it times 75%. And we're going to drop the 0.25, none necessary. So it's 3,554 VA. We add that to the list. Now, remember those 3 that we said, the clothes dryers and all this kind of stuff that we had? Okay, remember? We're gonna take those values and the parameters. Okay, so in this case, we do the 5,500 VA times 1,000. That's 5,500 VA total. Now, for 220.61, because remember, it made a reference and said that we can utilize 220.61 for these values that we're calculating in part 4 on this. Remember, it made that reference and said that we could. Okay. We're going to do that. So in this case here, we take the 5,500. It happens to be larger than 5,000 anyway under the standard method. So we're going to take the value that's larger and we're going to apply 70% to it. And that's going to give us 3,850 VA. Pretty simple. Now we're going to look at these cooking counter-mounted. Okay. Now this is where we go, okay, we lose this little benefit of just adding up nameplates now. Now we have to actually treat them like ranges, okay? We have to treat them like something, all right? And we have to compare the two. So again, first thing we do here is we look at that 7 kW counter-mounted cooking unit, cooktop. I should probably just say cooktop. And the 6 kW wall-mounted oven are included in this calculation, but both fall under the parameters of column B. The demand factor percentages found in that column for 2 units is 65%. Multiply the total kW, which is 13, by the demand factor percentage of 65%, because they both fall under that same column, and find the calculated load, okay, which is 8.45 kW. All right, you with me? All right, so in that case here, 8.45 is equal to 8,450 VA, or as we like to make it, and we can take that value times 70%, which is 5,915. Now, quickly, I want to do something real quick because it's been a while since I did this one. What we want to do now is, since we're doing this, I want to jump over to the code. I'll make sure y'all were seeing what I see. Yes, you are. Okay, cool. I got worried there. You notice my timing's been a little better tonight? Because I moved I figured out what I was doing wrong the other night. It takes a little bit of time. All right, so now we're going to jump back to the code book. And we're going to real quick do something that I want to make sure that I didn't screw up as I was converting this for tonight, because I did change a few things. Oops, right here. Okay, so real quick down here where, notice number 3 says where, over 1 3/4 through 8 3/4 kW, right? In lieu of the method in column C, it shall be permissible to add the nameplate ratings of all the cooking appliances rated more than 1 3/4, but not more than 8 3/4. And I think both of ours were, one was 7 and one was 6. And multiply the sum by the demand factor in column A or B for the given number of appliances. Now, it says where the ratings of cooking appliances fall under both column A and B, the demand factors for each column shall be applied. So that doesn't apply to us. What's more important to me is this part. Column C is used in all cases except otherwise permitted in note 3. Now, in our case right here, I want to show something that's people ask me all the time about. I want to compare the two. So the reason I'm going to do this is I want to show you something. And it not letting me highlight for some reason. Oh, there it is. And you look at this. This is in lieu of C. Okay? But many people ask me, well, wait a minute. Don't you take the cooktop and the range and add them together? You do for branch circuit loads. But you're not doing that when it comes to this application. You're comparing the two. So if I were to use C, because it says to use C, other than the note 3 allows me to use column B and compare it against it, I would have to go with 2 appliances because nothing in there allows me to add those 2 together and treat it like a range. I can do that for branch circuits, but I can't do that for the service and load calculation. So that would be 11 kW. Well, the way that I did it, I'm utilizing 65%, so it's a better value. You with me? So that's just in case people ask, because there has people that asked that before, okay? So people bring that up to me, and I want to remind them that we're not doing a branch circuit calculation here. We're doing a load calculation, and nothing in note 3 allows me to do that coupling effect that we do with the branch circuit, okay? I can't take all these ovens and mash them together with the cooktop and treat it as a range. You with me? I don't get that direction. So it would be 11 kW versus what we calculated, and we just calculated out at 8,450, 8.45 kW, right? I want to use the 8.45. I don't want to use the 11. I want to use this. So that's how we got it. So just in case you wondered, people ask that all the time. So now I do that at 70%, and that is 5,915. Okay? So in this case, now that part's done for my neutral. I write that number down. Now I need to look at my loads. And now since we're going back to the standard method for this, and I'm not gonna utilize the air compressor because that's 230 volt, right? Doesn't come into play. I'm just looking at my loads that are neutral loads. All right? So in this case here, I have a 3.2 amperes at 115 volts, and I have a condenser motor at 2 amperes at 115 volts. Okay? And so I would add, if those are my neutral loads, then I would simply convert them into their VA. And so this one here is, let's see, the air conditioning compressor was at 16.2 amperes, 3818. But we did not count it since it was a 230 volt load, so we didn't count that one. The condenser motor is 2 amperes times 115 volts is 230 VA. And lastly, that air handler blower motor was 3.2 amperes at 115 is 3.68. Now here's another question that comes up to me. People ask all the time. Didn't you get rid of the air conditioning in lieu of the heat? That is true. However, that is for our load calculation. When I'm running the actual calculations and the heat is going, the neutral load is still going to be seen. We did that for the ungrounded conductors, but we're talking neutrals. So there is indeed neutral current that we have to account for. Okay? So that's why we use it here. And people ask me that question all the time. So that's why we're picking this back up in order to pick up that neutral load. Okay? It is considered an appliance, Robbie, but it's 230. It doesn't have a neutral load, so it's not going to come into play in what we're working on right now. All right? So in this case here, that was going to give us 598. So the last thing we need to calculate is the largest motor. Okay? Now, interesting enough, we picked up all the motors in the optional method, but we didn't have to do anything that picks up the largest motor because we just took all the motors and we took them at their nameplate. Well, now that we have to do the neutral load, we have to jump back to the standard method. And then once we're back to the standard method, we still have to count for that 220.50. We have to take the largest motor that's going to have a neutral load to it. Okay? So we have to, since we did not use the heat since we did not use the heat, we look at all the motors and had to make that selection. Okay, and the heat was not 120 anyway, so wouldn't make a difference. Okay, the largest motor is usually the air conditioning motor. If the air conditioner load was omitted, we use the second largest motor. In this case, it was that half horsepower motor in that disposal. Okay, remember, it's the largest motor and only one is used, and the dishwasher is not going to count. Okay, that's appliance. We're not going to use that as the motor. Okay, that's the appliance. But a disposal, for example, is a pure motor in a sense. It just has a blade on it, but that is a motor. It's not in conjunction with other types of systems like you would with a dishwasher. Kind of find that odd, but again, we don't ever consider that appliance as that, to utilize a dishwasher, even if it was a higher amperage rating. We typically don't count that as the largest motor. Because to be honest with you, the motor that's probably in it is probably not the actual largest motor. The heater in there is probably what's doing most of the draw, by the way. So anyway, so the in-sync half horsepower, we went and got that value earlier. It's 9.8 amperes times 150. That's 1127 VA. That trash compactor was 900 VA. Those three attic fans was 1512 VA. Okay. But we only use one of them. We don't use all three of them. So any one of them would only have been 504. So that's not going to work for us. So it looks like that in-sync waste disposal is the largest motor load that is going to be utilizing a neutral. So in this case, it's 1127 VA. 25 times 0.25 is 281.72, or again, 282 after rounding. And I think we covered all of those loads. So when you crunch all the numbers, that's what we did for the general lighting. Remember, that came straight from what we did before. Nothing changed. We did the fixed appliances. That's where that value came from. Here's what we got for the dryer. Here's what we got for the cooking. Here's what we got for the air handler motor and condenser fan motor. And we took the largest motor that operates at 120 volts to get a neutral load. We take that, okay, and not sure what that is. And it is 282. I'm not sure what that 116 is. To be honest with you now. Oh, it's 150. Yeah, it's not, sorry, typo. All right, so we've got that value, and so we add them all up, and that is 21,247. Divide that by 240. It's 88.52. 0.5, we round to 89, and then we go looking for the conductor. And in that case, we're going to go, and you'll notice that if you go to 31015B16, a conductor, again, 75 degrees C column, we're going to look for a 3 copper or a 2 aluminum that's going to be able to handle that. And I think that is it for that. And I'll come back here and see any questions we might have on that. Anybody got any questions? Now it's time to ask some of your questions. Oh, I'm going to go back and look at some of your questions. And let me go back here and see for Robbie what you wanted, Rob. What did you say, DJ? Is that a mask or a panty? What you trying to say? All right, y'all, there it is. 210.23a exception. Okay, I'm going to go look at that. So let me scroll down if y'all have any additional questions. I don't think that's a lot longer for the neutral. You have to do all that for the neutral anyway. So it's the same amount of time it would take you to do the standard neutral. You can't use this, you can't use the optional to do it. So all we did was go do the standard method, and we only utilized those values that gave us neutrals. We didn't have to do all the other stuff because we're using the optional method. But we still had to use all the items in the standard method that deal with a neutral load. Those are the things that we wanted to capture. Okay? And that's what we do with the standard method. The optional method, we use that to get us there, our loads for our ungrounded conductors and that established. But when we go to do the grounded conductors or the neutrals, we're just pulling the values that have something that's going to put neutral current onto the actual, onto the grounded conductor. Okay. And so that's what we do for that. Okay. So, well, the only problem with that, Robbie, is if you're going to do the standard calculation every time, your services are always going to be larger than everybody else's. And if you're okay with that, that's fine. The optional method will always result in a smaller service. And I don't know about you, but I'm not usually, as a contractor, I'm not willing to give away copper or aluminum. I'm not willing to pay the extra upcharge it is to go from a 200 amp service to a 250 or 225 or to 300, whereas a standard method might put me as much as 60 to 100 amps higher than I would do with an optional method. I'm not willing to give that money away. And that doesn't make a neater installation. That's just money. That's just throwing money away, because the code allows me to do either or. And I'm always going to do the optional method. But we just have to remember that the neutral. Now, here's the good news. Typically, when you do an optional calculation and you're going to use, let's say, SE cables, then you're going to be bound to the size of the SE conductor that comes in there anyway. And the grounded conductor cannot be smaller than 2 sizes smaller than your ungrounded conductors. So again, it's not going to be that size anyway. Yeah, but you still have to make sure you calculate it to make sure that it's, Another thing that you got to remember is, even though we did that neutral calc, we still have to compare it. Okay, don't forget that. We still have to compare it to 250.102C. Remember? We still have to do that. Okay? Just remember, you still have to do that. And we're going to take whatever results in the larger of the two. I still got to go look at 210.23 exception. I will in a second. If you're asked to do a multifamily calculation and they don't mention a laundry circuit, would you apply 220.52B, or would you use Article 210.52F exception 1 or 2? So what Jay's talking about is whether or not you had a multifamily and they have a laundry or they have a laundry facility. So in all fairness, Jay, on an exam, they're not going to expect you to assume. They're going to tell you that each unit has a laundry, or they'll tell you a laundry facility is on site. And the reason they're telling you that a laundry facility is on site, so that you know that it doesn't have to be valued in when you're doing your calculation at 1500 VA. If it's a multifamily dwelling that does not have a laundry circuit, then you don't have to count the laundry circuit. Okay, and that's basically what the gist of that. Okay, but in an exam, they're going to tell you. Okay, now that's totally different if I was asked to do a single family dwelling. And if you were asked on an exam to do the calculation for a single family dwelling, then I would assume 1500 VA. If they ask you for something other than the general lighting and receptacle loads, if they tell you what is the calculated load for the dwelling and they give you all this information, the size of the dwelling and all this stuff, then I would consider them, and they don't tell you how many small appliances and they don't tell you about laundry, then you're going to assume those are there. Okay? You're going to assume that. So here's a quick test though, guys, that I want to give you a little tip. It's hard sometimes to get into the head of the person that's writing the exam. So when you're doing the calculation and you get in a question, Jay, let's say for it's a single family dwelling, do the calculation without the 1500 VA and do the question with the 1500 VA and see if the answer is given in one of the options. Believe it or not, sometimes it's good to use the questions, the answers, to validate the question. Okay, you with me? But if it was a one-family dwelling or something like that, or even as individual dwelling unit, and all they're asking me is about the dwelling unit, then I'm probably going to assume that it has a laundry circuit, depending on how they ask the question. But no, if it's a multifamily, they're going to tell you whether or not it's a laundry facility or not in their question. So I wouldn't worry too much about that. They're going to give you the information. They're not there. That's kind of a tricky question, and I don't see them doing that because that's not fair. And again, people think that the exams are designed to trick you. They're not supposed to. That wasn't our intent when we write them. It was the intent to try to give you as much information as we can so that you can answer the question. Because, you got to think about what tests are for, right? The tests are designed to just validate that you know how to navigate through the NEC. Not that you're a supertrician, right? That's all they're trying to validate. Okay? All right. So let me go real quick look at, I don't know if I answered your question the best I can. Let's see here. I can't remember again. What is it? I'm sorry, Robbie. It was, I'm having to scroll back because my mind is not, I'm not remembering it tonight. I think you said 210.23. There you go. 210.23a exception. Okay. All right. 210.23a exception. Let me go to the code. And we'll go to 210. And I'll see if I can explain it. Sometimes code even gets me confused all the time. So it's ain't the easiest document in the world to understand if y'all haven't gathered that yet. All right, 210.23a exception. Talking about this one here, Robbie. Okay, so what does A say? And let's get the premise of what we're talking about here. Permissible loads on a multi-outlet branch circuits. Okay, and incidentally, I will tell you guys, a single duplex receptacle is a multiple outlet branch circuit. Okay, all right. 15 or 20 amp branch circuits says a 15 or 20 amp branch circuit shall be permitted to supply lighting units or other utilization equipment or a combination of both and shall comply with 210.23a1 and A2. So this is basically telling me that, we'll start with this. This is basically telling me that my 15 or 20 amp branch circuits, people ask me this all the time. Can I put receptacles, for example, on lighting? And I'm like, yeah, why not? So people ask that all the time. Now, the only time you can't do that is a kitchen. You can't put your small appliance branch circuits on with your lighting. But in the bedroom, I can go around and hit all the receptacles and I can pop up and I can hit a luminaire all I want. Okay, that's perfectly fine. Other utilization equipment can be supplied. And again, utilization equipment is a definition for that. So that's other equipment. So this is just allowing me to supply other equipment. Okay. And that could, utilization equipment is very broad. Okay. There's a lot of things. Again, if you ask me to point out something specific, any type of utilization equipment, and we'd have to look at the definition, can be connected to a 15 or 20 amp branch circuit along with the lighting. It's fine. Now, of course, we got to use some common sense in the real world. Lighting is a fixed load. We know what the wattage is on that. Receptacles, we don't. Lighting is. So if we are going to put other utilization equipment on it, then all it's saying is, oh, by the way, if you're going to do that, you got to follow the rules in 210.23a1 and a2, which means if I'm going to put cord and plug connected equipment not fastened in place on these 15 amp branch circuits, then I'm going to have to limit it. Okay? I'm going to have to limit it to 80% of the branch circuit rating. And if it says utilization equipment that's fastened in place, I'm going to limit it to 50%. Now, let's get to your exception. It says exception. The small appliance branch circuits, laundry branch circuits, and bathroom branch circuits required in the dwelling units by 210.11c1, C2, and C3, that covers all those we just said, shall supply only the receptacle outlets specified in that section. So the exception is basically saying, you know how the A is telling you that I can have lighting and utilization loads and on the same circuit? We're not going to allow you to do that for the small appliance, kind of what I just said. The receptacles for the small appliance are only for those locations that's allowed. And that is receptacles in the dining room, pantries, kitchen. That's the only that's the only thing that can be on that circuit. You with me? And that's a receptacle circuit. Same thing for the laundry. All you can have is laundry, no other outlets. Okay. And receptacle outlets, by the way. And in the bathroom, it's exactly the same. The receptacle that serves the counter, the one that's within 3 feet of the sink basin, nothing else can be on that. I can't have lightings. I can't have the exhaust fan, which could qualify as utilization equipment. I can't have that on it. That's what that exception means. Okay. Now, I know you're going to probably tell me that's not the one you were asking about. So I'm going to come back again and see what. Nope, don't go there. This is just telling you have to follow the rules in 210.11 C1, C2, C3, and nothing else can be on it. All of those are 20 amp branch circuits. Small appliances, a minimum of 2. Laundry is a minimum of 1. And then, of course, you have the bathroom, which you don't have to do a VA for. That gets engulfed into it. Don't mix the rules that are up in 210.52, right? That is a receptacle, placement, spacing, all that kind of stuff. And 210.11 is the one that tells you you need to have the branch circuit for those applications. That's the 210.11. All this is reminding you is that, hey, I'm going to allow you on 15 and 20 amp general circuits to put lighting and other utilization equipment on that circuit, but we're going to let you do that. Okay? But if you're also going to do this, then you've got to follow the rules in A1 and A2, which is dealing with cord and plug connected equipment not fastened in place, as well as utilization equipment that is fastened in place that might be on with that 15 or 20 amp branch circuit. So because of that, it's going to limit the amount of current that can be on it. Okay? But that exception is just trying to remind you that, hey, bathroom circuit, small appliance circuit, laundry circuit, don't be trying to put the lighting on with it, okay, in that scenario. Now, there is an allowance in that rule for bathrooms, for example, whereas if my circuit doesn't leave that bathroom, if it doesn't leave the bathroom, then I can pick up the lighting and the receptacle, but it can't leave that bathroom. It's got to stay in that bathroom. Now, most of the homes that I wire or have wired, I just loop all the bathroom receptacles. And I've had people say, well, isn't the hairdryer going to blow up? How many hairdryers? I guess I never grew up with girls in the house. And my wife, I don't, just so y'all know, I haven't had to blow dry my hair for decades now. I'm just saying, okay? So I guess the concept for me as an electrician is the code allows me to do the one, the branch circuit for the receptacles serving the countertops in the bathroom. I just always looped them around, and I never had any problem with tripping breakers. But I know it happens. So again, I could run a separate branch circuit to every bathroom, and the code allows that, and I could actually pick up the lighting that's in that bathroom perfectly fine. Not a problem. Okay. But that's afforded me by that other rule. Okay. Now let's see here. Did I answer your question, Robbie? I want to make sure I answer your question. Just before I move on to anything. Just let me know. Yep. So thank you for clarifying. Okay. Hopefully I answer you. Again, anytime I answer something for you folks and you don't think it's clear, the difference between me and a lot of educators is I'm telling you, if it's not clear, ask it again, and so that I can clarify, right? Because I want to make the questions, I want to be clear, okay? All right. Let's see here. Oh, I know what I was going to do next. So I wanted to go over pull boxes. Just for those that get it confused, when we do box fill, okay? No, I'm not saying that. You're saying that. Don't put words in my mouth. The code requires in 210.11 that I have a circuit for the bathroom. Now, I could go from that bathroom receptacle to another bathroom receptacle, loop it to another. If you want to call that dedicated, The National Electrical Code doesn't use the word dedicated anymore. It's an individual branch circuit, okay, which you could translate as being dedicated if you want, but getting technical now. But I mean, it essentially is for that bathroom, okay, so you're right in that. Now, when it comes to appliances, again, the rule in 210.23, don't start intermingling that with all the rules that are up in other 210 locations, okay? Don't start intermixing those, okay? That's just a general statement in 210.23 about a 15 and 20 amp branch circuits and allowing me to have the lighting and utilization equipment on the same circuit on a 15 and 20 amp. That's fine. Then it only kicks in and says, well, we got to do something if you're dealing with a cord and plug connected, or you're dealing with a fixed utilization equipment that's fixed in place. If that's the case, then we need to limit the amount of current on that circuit. That's all that was saying. Okay. Now, when it comes to pull boxes, remember, pull boxes is different than a box fill calculation. When I got 4 gauge and larger, I'm going to be dealing with a pull box calculation. If I'm dealing with the 6 and smaller, I'm dealing with a box fill calculation. So I just wanted to bring that up because on an exam, they might give you something and you think that it's dealing with you might get a box like this. And now this is not to confuse with the requirements that you have for a wire fill for like a wireway or an auxiliary gutter, which is a totally different thing that we might go over one night, and I do a presentation on doing that cross-sectional sizing thing, which might be beneficial for you. But when we're talking pull boxes, they will ask you certain questions. And remember, this is all really about the trade size of the raceway coming in, okay? Now, another interesting thing is if I get a question like this, and it's, and we're doing something with the sizing, and it might be, for example, conductors that are 4 and larger, but they're using MC cable. Now, people will argue that how can you do a pull box calculation if it's an MC cable and you're not going to be pulling it, you're going to be splicing? Well, 314.28 also covers splicing as well. And it reminds you that and this is just little tips for you, if you have an MC cable, you need to convert that to what would be the equivalent trade size. So basically, you take all the conductors that are in that MC and you calculate it like you were going to do a raceway fill calculation to tell you what size raceway you would need. And then once you get that trade size value, then you can continue on with your calculation. So in case you didn't know that, and some people don't know that, so if you get an exam, and I've written an exam question like that in Texas for it, I will give you a calculation with splices in it, and it's being fed with the MC cable. And my intent is that you have to convert that MC cable into what size raceway would you need if it was running a raceway. And then only then can you do the calculation. So it throws one more step in there that many people screw up. Because MC cable, for example, doesn't come in trade size. It comes in ODs, diameters, okay? Many people want to say, well, it's trade size this. It's not. It's the OD, and it varies from manufacturer to manufacturers, right? All right, so anyway, if it's a straight pull like we see on the screen, just remember straight is 8. I think Tim said that. Straight is 8. Always remember that. Straight pull, straight is 8. 8 times. Okay, 8 times the raceway. And in this case here, I will go to here. It is this way. There's no other entries anywhere. This is it, here to here. Doesn't matter which way you go. This is trade size 3. This is trade size 3. 8 times 3. There you go. Okay, easy as pie for that. So in our case, 8 times 3, right, is 24. That means that I have to have 24-inch wide box, okay? Now, in this one here, interesting, on an exam, they might give you this equation. They might not even show you the wires, but again, a big controversy on what they'll show you. And I can tell you, there are some exams that they do not show you the wires, so you have to assume the worst case scenario, okay? I'm literally serious. So in this case, they come in with a raceway this way, and they come in with a raceway this way. So always remember that you have to do this way because it's the opposite side, and then you have to do this way to the opposite side and get those dimensions, right? So it's 6 times the largest raceway in the row. Okay? Now, if there was another raceway right here, then you take the largest one times 6 plus the sum of the other raceway that's in the same row. And if I have 2 separate rows by chance, because it's a deep box, then I do each row separately, and I take the row that provides me with the largest value. Okay? You with me? Because that'll be their worst case scenario. All right, so in that case here, and so you got to do dimension this way, 6 times trade size. This way, 6 times the largest raceway, this side. Now, you have to be careful. I'll bring this up because this is kind of one of those electrician things. You got to be real careful. Just because you size this box 6 times the largest raceway and 6 times the largest raceway this way, if those conductors come in and go out, okay, then the 2 conductors that are mutually together, that both contain the same conductors, you also have to have a space between them, okay? And so you have another dimension, and that dimension is 6 times from here, the largest raceway. So I've had people say my box was right, but then they put this raceway over here. And believe it or not, as an inspector, I literally had to fail people. They sized their box right? They did everything right. They want to cuss me out. But they didn't think about where they put their entries. And that screwed them heavily. Now, of course, if they already pulled the wire, they're really screwed. So ultimately, they end up having to cut them and splice them and move the raceway and plug the hole, and it becomes nasty. So a funny story, this actually happened in a data center, and they wanted to cut them because they screwed up in their spacing of their raceways. They had the dimensions and everything right, but they put the raceway, they didn't have it, right? And at the end of the day, they were going to splice them. But guess what? The engineer had designed these because of reliability for the data center for some really big company whose name will not be mentioned, and they probably are the browser I'm using. I'm just saying. But anyway, they would not allow splicing. Tell me that doesn't suck, because they can't just cut them and move it now. Wouldn't that suck? Probably should have done a little bit of thought ahead of time, because I remember them begging me for, it wasn't the first buy. I mean, it was a bunch of them begging me to let it go this time. That, okay, what we'll do is we'll come in and we'll make a big loop and we'll go. And I'm like, sorry, buddy. And look, I have no problem helping people out. But when I was an inspector, here's the thing. If it's written in black and white, now I can argue a code. We can argue code till we're blue in the face. But this one, for example, is written black and white. It's simple to follow. Just do it and take your time. It's simple to follow. Just remember, you have to figure all possibilities and take the worst case scenario. And I'll show you that in a second. Okay? All right. So in this case, the poor guy was kind of, it sucked for him, but everybody grows and learns through it. And next time, I guarantee you, he will never make that mistake again. Okay? All right. Let's go to the next. So now, same here. This is a U-pull. Now, both of these raceways contain the same conductors. Okay. All right. So again, I'm going to do 6 times the largest raceway. Now, I don't have to do this one, because if it's the same size raceway, then, it's going to result in the same value. But I do, since these are the same conductors, then I have this coming into play. Again, it's 6 times the largest raceway is the separation of raceways that contain the same conductors. Okay? So I'm good from here. So this might be, I don't know, if this is trade size 3, Then this would be 6 times 3. It would be 18 inches this way. So that dimension's this way. And then this way has to be at least 6 times the largest raceway between this entry to this entry. Okay? Now, of course, this is a box that's a little bigger than normal. That's fine. But it has to just be wide enough in order to accommodate the lock rings. You with me? So, in that dimension, because there's no other dimension. That's all we're dealing with in this minimum dimension. Okay? But I have to be able to be able to meet that. Now, on an exam, I'm not going to go out on a limb here, but I don't want to think that they want to throw you something like they might give you some dimensions, and then they might give you the raceway size, and then they want to know boxes. Well, the reason I throw this out at you, just to throw in, I don't know, we don't know what it'll be on an exam, but I want to tell you here that if they told me this was trade size 3, and this is all they gave me, and then they told me this was trade size 3, probably a little bad way for them to give it, but they could, all right? Then they wanted to know the box dimensions. Well, if this is trade size 3, and this is trade size 3, I'm going to go with that. And then I know that it's got to be 6 times 3, so I've got to have these got to be 18 inches apart. If I need to know the minimum dimensions, it might be 6 times 3, it's 18 this way. But in this case, it might be 18 between them, plus the 3, plus the other 3. So I might have a 16, 17, 18, 19, 16, 17, 18, 19, 20, 21, 22. So I might have a 18 by 22 because I have to accommodate the trade size 3 raceway. So I just want you, depending on how they ask the question, just be careful. Because if I were to just do this calculation and say it is 18 by 6 times 3 is 6, 12, 18 by 18, I would be wrong. Because that's the dimensional space that it has to be. Okay? That's this value from here to here. But I still have to have the box wide enough to accommodate the raceway itself, right? So don't fall into that trap. Don't let them, it's not a trick question. I just don't want you to fall into that trap. Remember, the raceways do take up dimension. Okay? So just don't, you know what? You got to remember who writes exam questions. Let me tell you a little secret. I helped write the exam questions with Texas for the 2017. We had about 30 people in the room. Most of them were master electricians. Every single one of them most of them wanted to write questions that were so damn hard that when we sat in the room and the people from PSI put the question on the board, it sometimes took people in the room 20 minutes to answer the question. And some of us couldn't answer, but we had the peer group. Is that fair to you? If they can't even answer it in 3 minutes, how should you be able to answer it in 3 minutes or 2 minutes? So we had to tell them and say, look, guys, the exam is not the same exam for somebody that's a master for 20, 25 years. This is the minimum entry. This is the minimum point in licensure. This is not for somebody that's 20 years seasoned master electrician. This is an entry level question. We don't have to get so deep. We're not trying to create supertricians here. You're going to do that once you get that license, and that's where the learning really begins. So we always had to reel these guys back and say, guys, calm down. That question is not even remotely something that an entry-level master electrician should have to pass. It's not. So again, somebody somewhere can have the mentality that they're going to write a question that's so freaking hard. Just be careful and analyze the question. And that's why I say, if they want to know the box dimensions, and they give you the values of the raceways, make sure you take into account the raceway. Okay? If they gave you, for example, a U-pull like this. All right? And then look at all your answers. Okay? Look at all your answers. Okay? So in this one here, no, because that's not an angle pull that we're using here. So you're not going to do 3 plus 3. Now, so this one here, is, so on the same side is, other one's the same. Now this is the same side, but this is utilizing the same. So it's just going to be 6 times the largest raceway on this side. Okay. If I'm doing an angle pull, I'm going to do that. Okay. But I'm not going to do that with a U-pull. Okay. So in this one, it's just going to be 6 times 3 this way. And this way, it's just going to be 6 times 3 and maintain that separation. And let's go look at the code. Oh, is that what you're saying, Jay? I'm sorry. Oh, I'm sorry, Jay. Yeah. I'm sorry. You were saying what I was saying. So yes, you got it. So here it would be, yes, the 6 times the 3 plus account for the actual raceway. Absolutely. Yes. Sorry, Jay. I thought you were talking about the where you add the side and then the other ones that are next to it. I'm sorry. Yep, you're right. Absolutely. Okay. Definitely. Very good. I should have known, Jay. You were on there. Let's see here. I'm glad that we got that cleared up too, Jay, because I was just getting ready to go to the code and explain to you why you don't do the largest raceway and the one in the same row for U-pulls. All right, let's see here. We got another one here. Very good. Okay. So in this one, for example, if you get something like this, I just want to show you how you would do this in exams. This is a really good graphic. Now, here's something. So you look out here because I'm showing you potential routing of conductors. But I can promise you, and I have seen it, in many exams, they do not give you the route of the conductors. They don't. They give you the raceways, and that is it. Okay? Now, you're good, Jay. You got it. So, I think what happened, Jay, is I started on a different topic and then came back and that type of thing. And Robbie clarified to get me back on track because I was going to go down a different road. And you saved me about 10 minutes of a lesson. So in this case right here, you might get a question on an exam that shows a box with 2 layers. The one on the right has 2 layers. And you got the top and the bottom. Now, here's the thing. You do not know which way these conductors could possibly run. So I've had a lot of people give me a bunch of crap. I did an article about a year ago. You can go look at it. If you're over on my LinkedIn channel, you can go look at the articles I wrote. Or if you're on the app that I have on our channel, or you go to my blog that's on our website, Master the NEC, you'll see a long article I wrote on this. Boy, I took a bunch of crap from people when I first wrote it because they say every exam would give you the route of the conductors. I can tell you they're full of crap because I wrote exams, right? They don't. We don't always tell you the route, but what we will do is make you size for the worst case scenario. So what you would do here, for example, if you're unlucky enough to get this one on your exam, just so you know. So I have 3 of them here, and these are in the same row. And this one is A, which is a 3 trade size. And then B, which is a 1.5. And then B here, that's also a 1.5 trade size. And then down here, these are all C, so these are all trade size 1. And then over here, I've got 2 rows. So the first row is all, trade size 1. And then the back row is A, B, and B. It's the same as these. So in your mind, logically, you were thinking these are going to go with these. So the conductor's coming out of here is going to go here. Right here is going to go here. Out of here is going to go here. And then these 3 match these 3. I mean, that's logically what you would think, right? I mean, you agree? Logically. But not always the case, and so we have to be very careful in how we calculate this. So calculate for worst case scenarios. So here's how I would do this, kind of give you the idea. Now, I'd start up here on this wall, and I'm going to measure to the opposite wall. So I've got the largest raceway, okay, is going to be A. And again, I'm not doing the sum because that's angle pull yet, okay? So I'm going to do A, which is in this case a 3. I'm going to do 3 times 8 to the opposite wall. So 3 times 8. And that's my dimension this way. And I'd write that down. Okay. Now, I don't have to go from this side this way because I know that 3 is larger than any of these. So it's going to be greater this way. So this way so far is done for me for that part. Okay. Here. That part. Now, I'm going to go over here. So I've got this dimension, and I just keep writing these down as you go. Over here now, I'm going to go from this side and do its opposite wall measurement. And so in this case, and while we're at it, let's do this because I want to, since we're making this a lesson, let me pull up this while we're doing a lesson and bring up the code. So we can do this little lesson. I wasn't going to go into this tonight, but you know what? I'm feeling frisky. Hey, baby. All right. So, boy, this is slow again. This is my supercomputer. It better not be doing that slow stuff. Okay. Where are we at, folks? Okay, here we go. Let's kind of follow the code. Let me make sure y'all can see that. Yep, you can. Okay. So we did the straight pulls, and straight is straight pull. The length of the box or conduit body shall not be less than 8 times the metric designator of the largest raceway. Okay. Now, interesting enough, we'll go back to this. We'll go back to our pull box real quick. Interesting enough, there is no straight this way. Okay, because there is no straight value. Okay. But at any rate, we want to do a calculation. So we're going to do a value this way. We did this way, and we're going to do this way. So this would be 3 here. With me? 3. So it's 3 times 8. So this one was 3 times 8 this way, 3 times 8 this way. What is it? 8, 16, 24. So far we look like it's 24 by 24, worst case scenario, right? Well, now we know that these are actually, this is the only plausible straight. These are angle pulls. Okay? So in this dimension here, we need to do an angle pull calculation. Okay? So remember, we did straights. 24 by 24 seems to be an adequate size so far. Okay, and this is not following the arrows. This is just a plausible, could some of them go this way? Yes. Okay, that type of scenario. But we're just kind of, nothing's going to go straight, so we're just kind of, we're going to have to do this measurement to the opposite wall. Okay, so anyway, we got all this measurement, so just bear with me. All right, now, we got 2 rows here. Well, I can tell you right now, if I was on an exam, that row 1 where it's CCC, I'm getting rid of it. It is not going to be the biggest value. Trust me. So why waste your time on it? I'm going to that back row. That back row is A, which is 3. And that's going to be 3 since we're talking angle pulls for this now. And we'll go back to the code to show you because we'll look at the angle pull. So for the angle pull, it says where splices or... Ooh, what the heck? What's going on with that? I didn't know I was on the whiteboard feature. Sorry about that. Let me get off of that. That'll drive me crazy. Okay. So, I didn't know I had the whiteboard up. Sorry. So, hey, wait a minute. That would be cool. Let me do that again. So, right here, where splices or where angle or U-pulls are made, the distance between each way entry inside the box or conduit body and the opposite wall of the box or conduit body shall not be less than 6 times the metric designator of the largest raceway in the row. Okay? And it says this distance... Oh, crap. I thought it was a highlighter. It says this distance shall be increased for additional entries by the amount of the sum of the diameters of all the other raceways entries in the same row on the same wall of the box. Okay? You with me? You feel me? Okay. You ready? All right, now, let's get back to where we were. I can remember where I was at. Okay, so here we are. So in this case right here, this one would have been irrelevant because we really don't have a straight pull. And so we're going to do this. So here we've got, this was 3 times 6, right? So this is 3 times 6, 3 times 6 is 18. And in each one of these B's were a half, or 1.5, right? So that is 1, 2, 3. Plus 3 equals 21. Okay? So there is no, so here's where people will say to me next. Hold on. Okay, Paul, remember when you said there was a 24 this way and 24 this way? Well, there isn't really a straight pull. I'm starting out with dimensions that are going to be what I'm going to work with. But ultimately, there isn't a straight pull. Okay? Because I have no raceway on the other side. So it's going to be regardless, it's going to be an angle pull. Okay? This way is a straight pull plausibility. This way is no straight pull plausibility. So I started out saying 24 this way. I'm going to say 24 this way as a worst case scenario because this is a trade size 3, but I know that something's going to happen. But the reason I say that is, in this case, if I had gone in a real world, if I had gone with a 24 by 24, I would be compliant. In an exam, you're not, because they want the best plausible answer. So in this case, it would be 3 times 6 is 18, 19, 20, and then the 2 halves is 21. So this would be a 24 by 21 box. And I don't have to worry about this row because this row is greater than what this row would be. Okay? All right. That was a long way around trying to show you examples, but that's how I usually tell people to start. Now, if you want to get real efficient in your exam, then you would have looked at that right away and realized that the only thing you've got is one plausible straight pull and everything else is angle pulls. And it just saves you some time. I just wanted to show you, I wanted you to work it from the biggest value that you could have and work it down to what your actual result is. Let's see, here we have some questions here, man. You really got to be careful when adding raceways to existing cans. Absolutely. Yes, you do, buddy, because if that can is already set in place and you start adding another raceway, which people do all the time, right? How many of you have ever seen people go in and say, hey, I need to add another one to this one? Then I could, then you create a problem because you don't think about all those factors into it. So yeah, it can suck. Okay. We did get, you might mean the depth. You don't mean the width, right? Because what we've calculated is the length this way and the height this way. You mean the depth? Is that what you're asking about? What's the depth for this? I'll wait for Robbie to clarify if he's asking about the depth. Because right now, the width is certain and we have the height. All right, so here's the thing, Robbie. Good question. There's nothing in the code that dictates the depth. The depth has to be adequately deep enough to handle the raceways. So in this case, since it's 2 rows, it would have to be deep enough to facilitate the 2 rows. But there isn't a depth requirement. Now, most of the time, if you're going to buy a box that's 24 by 21, which if you're going to buy standard size boxes, you're probably going to get a 24 by 24, then your depth is already going to be taking care of itself. But if there was only 1 row, and I had trade size 3 going in the back there, say that 2 rows wasn't there on the right, just 1, then my depth would only have to be deep enough to facilitate the trade size 3 raceway. Now that's not to confuse when you come into the back of the box. So if I come into the back of the box here, then we're going to have some depth requirements on that because you have a removable cover on the opposite wall or not that comes in through the back, right? So if I come into the back, then I do have some depth requirements that we need to think about. So if I go to the code in that, okay, and this is the exception, says where the raceway or cable entry is in the wall of the box, car condo body opposite a removable cover, that would be like the back. It says the distance from the wall to the cover shall be permitted to comply with the distance requirements for one wire per terminal in table 312.6a. So I only have to use the values that are in the one wire table. So if I'm coming in the back with, say, 500 kc mills, and I'm coming in the back, and you want to know what the depth is because I'm coming in the back, and I might have coming in the sides, the top, but also coming in the back, and I did my sizing based on the sides and top, but now I've got something coming in the back. This is what's going to dictate my depth for this occasion only, and that means I got to go to table 312.6a. So we'll go to 312.6a so you can see it. And in 312.6a, you use the one terminal. So if it was 500 kc mil, for example, coming in, copper, then it would be 500 kc mil. It has to have it, the box would have to be at least 6 inches deep between the point coming into the back and the removable cover. And that's how you do that, okay? Always remember that it's still got to be deep enough to handle the entries that are coming into the sides. But if you're coming into the side that's opposite a removable cover, and it's got to be a removable cover somewhere, folks, okay, no brainer, then this is where you would come here, okay? Very good question. Glad you brought that up. Definitely. Definitely glad you brought that up. Let's see here. Brian says 314.24. So, Brian, you're gonna force me to look at the code and see what you're talking about. See whether it's relevant to what we're talking about. Since you brought it up. So this is the depth of the box. This is outlet and device boxes shall have an approved depth to allow equipment installed within them and to be mounted properly and within the likelihood of damage to conductors within the box. A little different than what we're dealing with in this application here, but you still do have to have the adequate depth, no doubt. Okay, and it does give for large equipment, it does give some minimum depths, but these are more or less minimum depths, right? We still have to have the depth that's going to accommodate the rules. Okay, so we still have to have the depth as well. Okay. Let's see here. A couple other questions, but good point, Brian, because we do have depth requirement. We have to do minimum requirements, and that could be on an exam. I'm going to be honest with you. I have seen that on an exam where they just want to know the minimum depth of a device box or something like that. So again, just kind of be aware of those type of things. What's the question here? I have... When you have... I'm sorry. Hold on, guys. Let me go back because I can't see the question. Says Demetrio, it says, I have 4 men who told me that when you have nailies on the conduit, he creates Walter's drop. I have no idea what you're saying. I'm sorry. I have no idea what you're trying to convey, Demetrio. Sorry. Let's see here. What else do we got here? Jay, hold on. I got to look and save because it's let's see here. Jay says 314.24b2 would refer to 4 and larger. Yes. So let's look at the code here. All right, see here. Oh, you're talking about 2 down here. Conductors larger boxes that enclose devices or utilization equipment supplied by conductors larger than 4 shall be identified for their purpose. Yeah, but that's not what we're doing in a box calculation, because we're not putting devices in there. We're not putting utilization equipment in there. Obviously, the boxes always have to be deep enough to handle whatever you're going to put in there. You know what I'm saying? Too late, Jay. We're already there, buddy. So boxes automatically have to be deep enough to handle whatever you're going to put into. So that's kind of a general statement. But on an exam, just remember that if it's a pool calculation, straight is 8. Angles is 6, U's are 6 between, that type of thing. You know what I'm saying? Just remember that. Let's see. Now I'll try to translate again, Demetrio, what you're saying. That you said 90. So I'm going to try to, when you have 90 degrees, he creates voltage drop. All right, so there's a guy that's just talking out of his butt, Demetrio. He doesn't know what he's talking about. Because I'm not sure in the code, 90 degrees or whatever, that type of thing has nothing to do with voltage drop. I'm not sure. How about this, Demetrio? Rewrite your question a little bit better and submit it, because none of that's making any sense. I'm sorry, I can't understand it. I think it's 1/4 or 1/8 space behind the device. So what you're talking about, Bobby, is the space behind it that you're required to have. Let's say if it's in a wet location. Is that what you're talking about? And so if that's your question, then that is actually that's going to be up here in the beginning. That's going to have for wet and damp locations. Here's 1/4 inch. Okay. So it says, let's see here for the space. Let's see here. Approved drainage openings not smaller than 1/8 of an inch and not larger than 1/4. Okay, for that's not really what we're talking about for that. It's not really what if that's what you're talking about. No. We're talking about for water drainage. I would think I'm the gap between. I would think, isn't that what you're talking about? The gap requirement. Not sure if that's what you're talking about, but if you're talking about that little gap that's required to be in there. So that's the air gap, and that's usually built into the enclosures, but it's a 1/4 inch. For the life of me, I'm not seeing it. Not seeing it in my code, and daggone, I know it's in here. For my spacing requirement, although I know where it is for cabinets. Okay. So I'm not sure where I'm seeing it, but I'm telling you it's 1/4 inch if it's wet, but it's generally dealing with cabinets. But I'm drawing a freaking blank tonight when it comes to what in the heck is going on? Where in the freaking... I should probably go use the index, shouldn't I? For some reason I'm drawing Oh, there it is. I'm sorry. So typically when we get the cabinets, cutout boxes, and all that stuff, when you mount them, that you mount them in 1/4 inch airspace between the enclosure and the wall. Okay? For that. Now, that's for cabinets, cutout boxes, and meter sockets. When I get to 314, it basically tells me that when I'm dealing in a wet location, it says in a damp wet location, boxes, condo bodies, fittings shall be placed and equipped so as to prevent moisture from entering the box, but and all that kind of stuff. And it has drainage, but you don't have the same requirement for the air gap as you do for that. Okay? It's not in here. I don't know why I was thinking that. Now, something funny is if you go look at EMT. So you go look at EMT, and I think it's EMT, in wet locations, all supports, bolt straps protected from against corrosion or corrosion material. And I guess it's 300.6 that it would require you to have some potential separation, but I don't think that we put those right on the wall all the time. It's just the cabinets that has the requirement, cabinet cutout boxes and meter enclosures that have the requirement for a 1/4 inch gap. I'm not sure that's what you're asking, but that's the only thing I can think of. I don't know I have no idea what a nailies is. Oh, you mean the gap behind the box? In the back of the box? I think that's what might be what you're talking about. Okay. Well, skip down here to boxes. We've already covered the devices and whatnot. Let's see here. Non-metallic boxes. And we already get that. 4 and larger. Boxes, brackets, screws, mounting. Y'all all are pretty familiar with that stuff. I don't need to add anything to there. Depth of boxes, we just covered. I don't think there's anything else that I want to add. Large boxes, conductors. And your depth in the boxes and all this stuff, I guess that's what you're talking about, is all here. Boxes enclosed devices, utilization equipment, supplying blah, 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 shall have a depth of not less than 2 1/16. 12 and 10, where the equipment projects rearway from the mount of the box by more than 1 inch. The box shall have a depth of not less than that of the equipment plus a 1/4 inch. Okay. This is mainly for your device boxes, by the way. I mean, this is what's going to probably be your normal box. You're never going to, the only time you might run into a problem here is in this scenario where you're trying to put a range box in there, something like that. And you got to have a minimum internal depth for that. Okay. What else? 14 and smaller. I don't know when you'd get smaller than 14 in this case, but boxes that enclose devices or utilization equipment supplied by 14 gauge or smaller. Let's say it's a receptacle. Shall have a depth of not less than 5/16 of an inch. So those different questions, all good questions. Not sure that's what everybody was asking, but good questions. But I'm not sure I don't know what a nailie is or whatever that. I'm not even sure what that is. Oh, that's what okay. That's what you're referring to, Bobby. Okay, good. Now, the 1/8 of an inch thing, Jay, is dealing with the boxes. That's a good one, too. You might get that. That's low-hanging fruit on an exam. Y'all love me saying low-hanging fruit. But that is low-hanging fruit. Let's look at that just so you can, what he's talking about is, hold on here. Let me go back. Give me a second real quick. Hold on, 15 to 21. Did I go too far? I hate PDFs. Drive me crazy. Okay, here we go. Yes. All right. So these are low-hanging ones on an exam, maybe, I guess. So I have flush-mounted installations. Okay, so this is where it's going to be in the wall. Okay, it's not, so it's flush mount. So I'm going to put cover flush on it. It says installations within or behind a surface of concrete, tile, gypsum, plaster, or other non-combustible material, includes boxes employing flush-mounted covers or faceplates, shall be made so that the front edge of the box, plaster ring or extension ring, or listed extender will not be set back from the finished surface more than 1/4 inch. So I can have a box that's designed to be recessed. I guess that's the easiest way to say it, a recessed box. And I put a finish cover, just like every receptacle we put in a wall. That's a better example. That is a flush mount installation. Whereas if I mounted a box on the surface of the gypsum, that would be or block wall or concrete wall, that's a surface mount, right? And so this is dealing with the flush mount scenario, okay? So I can have a 1/4 inch if it's non-combustible material. It can be sitting back in a little bit, 1/4 inch. However, if the surface is combustible, then it can't sit back at all. It's got to be even with it, or it extends beyond it. Now, extending beyond it would really screw you up if you got a cover and extends too much and that cover can't go, and then you end up have a gap and you look like a jackleg. But at the end of the day, maybe here's what really happened, and you know this is what happened. You put it in right. The plumber came along and moved it, right? Because they do, right? Because they do. And now you get back to do your trim out and the daggone box is sitting out. And you're like, what? Now, don't go getting no Dremel and try to cut off the edge of the plastic or whatever it is. Don't be doing it, okay? But at the end of the day, yeah, can't be sitting back more than 1/4 of an inch if it's a non-combustible, and it's got to be flush if it's combustible. Now, the other one is the 1/8 of an inch, okay? And that 1/8 of an inch has to do with the gap around the box, right? Okay. Yeah, so F-clips. Many people call them things by so many names. But, some people will take those things and basically knock the box loose or take the Sawzall, go in there and cut the nails if it's nailed so the box is swinging. And then they'll use clips to hold it in place, the F-clips. Or I've known some people that just will at that point take the wires loose, pull the box out, and replace the box with an old work box. I mean, however you get it done, but don't try to put that cover on it and have it extend out, because there's another rule that requires that faceplate to sit flush with the surface. So that's another rule that's covered up in the requirements for 404 and 406, okay? Whether it's switches or receptacles. So you do one thing and you end up screwing something else, okay? What is that? You're filling their pipes with blue wire nuts? That's the big ones. Those big blue ones, the huge ones? Absolutely. And then they wonder, well, what happened? And then there's no question who did it, because who has wire nuts but us, electricians, right? Okay. So that's probably all we'll cover tonight. I was also, as you can see, I was going to go into transformers a little bit. I just don't have time to do it tonight. And these are some of my transformer graphics that you've probably seen before. That one is not. That was given to me. And I talk about different connections. And wow, it's sloppy looking right there, isn't it? Isn't this right here? Isn't this right here? Just look, what is this? Anyway, sorry about that. I went off on a tangent. So, I mean, I was going to, obviously we could show tap rules, 25-foot tap rules, or secondary conductor rules, I should say. Transformer secondary conductor rules on a transformer and blah, blah, blah. We don't got time tonight. I'm tired, so I don't want to go there. But at some point, we'll go there. And so here's what I want to challenge you guys, okay? Here's my call to action for you. You ready? My call to action is I want to do some Q&A sessions. I want to answer your questions and weird questions, whatever you've run into. And so email me some questions that you would like answered, and I will do a presentation and we'll do a Q&A. I'll answer your questions and whatever they might be. Transformer questions, motor questions, whatever it is you got. Send them to me, and I'll do a session. We'll have a code session. Okay, let me get back to real quick before we leave, because I appreciate all you and your time. Let's look at Demetrio's question here. It says, my foreman told me that 90-degree bends on a conduit create voltage drop. I told him that's not true, and I have not seen that in the code book, and it's not. I also told him about how to select the pull box. Pull box. I got that one, Demetrio. How to select the pull box. Okay. And so my email is, all this time, y'all don't know what my email is. Info, INFO, at masterthenec.com. Or you could go to the website, Robbie, and click the Contact Us button, And you can send it right from the website if you want to. And it's easier to fill in the blank box, and you don't have to go open up your web email and all that. If you want to do that, it works too. But send me your questions, and I'll put together some Q&A. I'll answer all those questions, whether you wanted to know. For example, you might want to know, how is 208, 120, 208, how's that derived? We shouldn't say derived because people hate that word. It's not really derived. It is what it is. So how is that done? And, and what's the difference between 277, 480 versus, or ungrounded versus grounded systems, or I don't know, whatever questions you want to ask, feel free to ask and send them to me, and I'll try to work them into a session. But Demetrio, the 90 degrees, you're not supposed to have more than 4 90 degrees between pull points. 90, you can't increase the voltage drop because of the 90s. Oh, I know. I knew with Demetrio. I'm like, I knew that. But in reality, you're not deceived 90. But what's going to voltage drop has nothing to do with the 90s. It has everything to do with the length. So if I had 1,000 feet, but I had 4 90s, it's not going to be any different than if I had 1,000 feet. You know what I mean? If I had 1,000 feet without any 90s, it's still 1,000 feet, and that's what voltage drop is all about. You know what I mean? Interesting thing about voltage drop is people don't realize that if I increase those conductors for any reason, I now have to do a calculation and have to increase the size. I shouldn't say for any reason. If I increase the size of ungrounded conductors because of voltage drop, or the engineer makes me increase it for whatever reason they may want to, for their own whatever, then I have to do a calculation, and I have to increase the size of the equipment grounding conductor proportional. And so maybe one night I'll go through and show y'all how to do those calculations, unless you already know how to do those calculations. I'll show you how to do some of those conversion calculations if that's what y'all want, because that could be on an exam. They might give you a size of a load, then they might tell you it's 1,000 feet, and they might give you all this information, and then they tell you what the equipment grounding conductor is, because you should know what it is based on the overcurrent device that they tell you it is in the question. They're going to want you to size that equipment grounding conductor based on the increased ratio. Okay? And so that is under 250.122B. So if y'all want that, send me a question and I'll do a question answer. So I want to do some of those too. Okay? Because again, it's challenging for me when I do these exam prep stuff to come up with topics, because I cover this stuff so much. And so, we've looked up code questions. We've done that. Everybody enjoys those. We've done some examples on ranges. I've done examples on dryers. I've done single family. I've done multifamily. I've done a commercial before. You tell me what you want me to do. But keep it in the realm of exam prep. You with me? Keep it in the realm of that. Okay? Now, if you want to do a Q&A and you just want to ask me any question that you ever wanted to ask, like, how does electricity really work? Whether you have protons and neutrons in the nucleus, and you have electrons in the outer valence shell that's constantly moving. Then you have what's called magnetic attraction that keeps the protons connected to the electrons. What happens when we apply pressure, which is voltage? It causes a spontaneous reaction to those electrons, whereas they get moved out of their orbit, and they get picked up by the opposing atom, who just lost its electron. So now it's trying to attract that electron to come back into balanced state. That's how electricity works. I don't know if you want stuff like that. I can do that too. I just have never been really, lately people don't want that. I'm an exam prep kind of guy. Okay. But if you want one night, we'll do. Okay. There you go, Gustavo. I don't know if I saw you earlier in here, Gustavo, but thanks for coming. Do voltage drop calculation. We'll do some voltage drop. And I actually have a presentation that I can do for voltage drop. If y'all want voltage drop, we'll knock out, because there's more than just 2 or 3 ways to do voltage drop. Okay? And sadly, that is on every exam, right? Even though we know that the code, hey, I got a trivia question for you guys. Where in the code is voltage drop required? Hey, grounding and bonding, I got a good one. Hey, I think I've got one coming up. Hold I want to tell you about this real quick. Y'all, but answer my question. Where is voltage drop a requirement to be considered in the National Electrical Code? While I check something real quick. Bear with me, guys. Y'all, give me that answer while I look something up real quick. I got to go to my own website to see what my topic is for tomorrow night. Oh, hey, tomorrow night on Electrician Live, I'm going to be talking service bonding. Okay? And for anybody that hasn't been to our website, that's what it looks like on your device. Okay? I'm going to be talking service bonding. So we're going to be talking 250.90, 90, 92, 97, 94, 250. Now we're going to be all of that. All of that. So join us tomorrow night. We'll be talking about, assured bonding for services, and we'll be talking about feeders and why you have to do things different. We'll be talking about concentric and eccentric knockouts, and we're gonna make service bonding for you guys so clear tomorrow night that you're gonna be like, it'd be like, ooh. So yes, Brian, absolutely, fire pumps. Also, no, I don't care, Jay. If you want to ask some 2020 stuff, feel free. Definitely. Go for it. Because that's just going to be a Q&A session. So, I mean, hopefully it won't screw people up when it comes to exam prep. But I'll tell you, it's 2020, and it probably didn't change much unless you're going to ask me, something that's definitely different. That's right, Tim. I got my core guys. And they're all right there on the screen, right there at the same time. Okay. So, voltage drop. There's a lot of places. 647.4? Hold on. All right, hold on. Hold on. Hold on. Let me highlight it for you. The voltage drop on any branch circuit shall not exceed 1.5%. The combined voltage drop of a feeder and branch circuit conductor shall not exceed 2.5%. I was banking. You just stole my freaking thunder, man. I was banking that nobody. You must have. What did you do? Do you have a electronic version and you typed that in? I was banking that nobody would know that under sensitive electronic equipment. I thought everybody would say fire pumps and emergency circuits, right? I didn't think anybody would say 647. So. Now, I am going to be hopefully putting in a proposal for the 2023 to bring voltage drop as a mandatory requirement. I know you're saying it's just because I work for a wire and cable guy and I'm trying to increase the size of the conductors. That is not true. That is not true. To me, voltage drop is a safety concern. Because if a piece of equipment is not getting a level of voltage it needs for safe operation, then it can overheat and it can prematurely fail. And if it prematurely fails, it could burn up and it could create a safety concern. So I think, and look, the energy code requires it. And you know what? The energy code is mandated by the local officials anyway. So even though the NEC doesn't require it for most normal applications, it makes it as a recommendation. Then the real problem is the energy code still requires it. So how many electricians are taking that into account? And we're just probably ignoring the energy code's mandated requirements, the IECC requirements, or that type of thing. So in order to get rid of this confusion, let's bring voltage drop into the code. We all do it. Most of you do it anyway because you know that's there. I tell you, I get a lot of questions on voltage drop. And then I have to look at people and go, but voltage drop is only a recommendation for most of our general applications other than, again, 647 and in 695 and all that. I said, and 700. Other than that, it's everywhere else. It's a recommendation, right? But energy code's going to require it. So are electricians taking that into account? Or are they going, hey, it's not in my NEC, I ain't touching it? So again, we got to get that corrected. So I think it should either get it out of the energy code or we need to add it mandatory into the NEC. Now, my problem is I don't know that I have enough energy to take all of the locations in the code that need to have that and write proposal or public inputs for that. I don't know that I have the energy to waste to do that. I've already written 20 plus and submitted them. I don't know that we'll see. We'll see. I still got time. I got another month or two. Oh, is that where you came across it, Jay? Stumbled on it? There you go. Sometimes the best ones are stumbled on it, especially as you're going through the code. Robbie says, because sometimes it's safer to not have grounding. I don't know if I agree with that statement, Robbie. Give me an example. Because even in an ungrounded system, I still have equipment grounding. So you have to quantify that statement to me. Since I serve on code making panel 5 that deals with grounding and bonding, I am interested in that statement. Because I don't know when it would be safer to not ground. To be honest with you. I can't think of it. But I might be just having my overly amount of orange tonight. And, okay. When wiring a lamp pole, I'm not even sure I understand that. When wiring a lamp pole, are you talking about like parking lot lighting? You're required to have an equipment grounding connector to that, so it'd have to be grounded. It'd have to have grounding involved in it. In fact, indirectly, any system that's originated from a grounded system is grounded. There is a grounded conductor. Okay? Now, I can have ungrounded systems, but I need to have an equipment grounding conductor. Okay? That type of thing. Yeah, but we have to have the ability to clear an overcurrent device. So and if you ground it, and since it's connected, it's an interesting point. If you follow equipment grounding conductor, which is really just a big bonding conductor, all the way back to the source, the reason we're doing that is put it at the same potential as the earth. If you remove that equipment ground, the earth is at a different potential. It's not at the same potential. So again, you have a greater risk of being shocked without an equipment grounding conductor run to that. Okay. So, I don't know. I don't know about that. So what is your answer on the voltage drop requirement under the NEC? What specifically is required to have voltage drop calculations? Thought I answered that. So you have voltage drop is obviously here in 647. You're required in 695 to do that for fire pumps, and emergency systems have a voltage drop requirement. Other than that, everything else is a recommendation. In fact, let's do something I like to do sometimes. Let's do this. What are we on real quick, guys? Now that we're just playing around here, I'm going to go back up. If you ever get an opportunity to do this, see where I'm at the beginning here? Watch this. Find. See what comes up when I do this. Let me see if y'all can see that. Yeah, you should be able to see that. Yeah, so real quick, Robbie. Yep, 3% branch, 5% for the whole. So that could mean 3 for the branch, 2 for a feeder. Or be honest with you, it could be 2 for the branch, 3 for the feeder. It's 5 overall, but you just have to be aware that it's 3. You could have a branch and a feeder involved in it in this scenario. It's 5 overall. So whatever you do for the branch, the feeder gets the off balance of that. So if you only have branch, okay, then you do it that way. All right. So anyway, what I was going to talk about here is this. So watch this. So here's voltage drop. It's under an informational note. It's great information, but not enforceable. Watch this. Here it is again under an informational. I don't know if y'all have ever done this before. Informational note. Here it's under an informational note again in the 310. Just good information. There it is under informational note again. Another informational note. Now here it is under 40. It's an informational note. Here it is again, informational note. And this is all grayed out. So this is D. Yep, still an informational note. Informational note. Again, remembering that informational notes are not enforceable. Now, here's your 647. Very good. And that's a lot of freaking voltage drop talking about in that one. It takes a while to get back. Now, anything additional, that's an informational note. Not applicable. And here's a PV. Now, this is talking about, this is more blatant. This isn't giving you a percentage. What this is telling you that when you're sizing the equipment grounding conductor, for example, and you're increasing the equipment grounding conductor to address the voltage drop considerations, it says it shall not be required for that. So, I mean, that's not what we're talking about, 3%, 5%. That's not what it's talking about. So that one doesn't count. And here's your fire pump requirement. Conductors and fire pump shall have a maximum capacity in accordance with 430.22 and shall comply with the voltage drop requirements of 695.7. So we haven't gotten to 7, but there's that one. And this one deals with shall not drop more than 15% below the normal under motor starting conditions. So there's your voltage drop there. And there's your voltage shall not drop below 5%, the voltage rating at the terminals. So, I mean, there's your voltage drop there. Let's go a little further. That's a 706. Actually, I stand corrected. That's even reduced it. It's not an emergency. So that's not. So it's fire pumps, and it's mandated in the sensitive equipment. There you go. I must have done a bad search at one point in my career. Okay. I can tell you that engineers are going to make you take it in consideration for most of them that I dealt with, or going to put it on their drawings anyway, or when the engineer calls it out, then it is what it is. They're probably going to require it for emergency systems to make sure you have the voltage drop. But other than that, it looks like it's not actually in there as a requirement. Just the fire pumps have their own rules. Sensitive electronic equipment have their own rules. But other than that, everything else is informational note, good information, but not a requirement. Just from being a bear in mind again that the energy code might have things to consider otherwise. Okay. Okay. All right, Robbie, I'm going to have to go down this path with you. I didn't want to go down this path with you. Okay. The earth is never to be used as anything to clear any breaker. It doesn't remove the hazard. Just because the lamp pole is buried in the earth, electricity is never trying to get to the earth. It's trying to get back to the source. So making a connection to earth is never, ever going to take the place of an equipment grounding conductor. And that's what we're talking about when we're talking about grounding, okay, and bonding, okay. The connection into the earth, that is called a supplemental electrode. That's a grounding electrode that's not required by the code, but people put it there anyway because engineers think that if lightning strikes the pole, it might keep the base from cracking and it can dissipate the energy in the earth. It never, ever, no. You never, ever, Robbie, never, ever, ever, ever can use the earth. Ever, never, ever can use the earth as a return path for grounding. Never, ever. Please do not do that. Okay? You cannot substitute the earth for any of that. Okay? Never, ever, ever, ever do that. Okay? Right here. The earth shall not be considered an effective ground fault current path. Ever. You never consider the earth as a path. Okay? Never. The impedance is too high. It would never clear a breaker. Ever. Let's do an example. If I have a ground rod at a pole and I didn't run and I had the circuit running out there. Remember, we don't care if the pole burns up. I could care crapless. It's all about protecting people's lives. So let's do a little calculation. Let's say that it's a 25 ohm, perfect world, 25 ohm ground rod. And it's a 120 volt circuit that's going to that pole light. So we know that it's 25 ohms. And we know that it's 120 volts. Okay? So we're going to do, let's see here, let's just go 25. Oops, hold on here. What's wrong with my calculator? Hey, what the heck? Hold on for a second. I got to get a different calculator. I just want to show you. Hold on for a second. Damn thing's not working. Hold on. Where's my calculator at? Okay. Okay, I'm back. Okay. Sorry. Okay, so what we've got is we got EIR, the equation. E over I times R, right? So we got E 120 divided by 25 is 4.8 amps. 4.8 amps will never clear a 15 amp, much less a 20 amp overcurrent device. It's never going to happen. So even if the measurement on a ground rod was 25 ohms, okay, and it's never going to clear a device, and that's what we're here to do, right? We're here to clear the device. So there is a lot of times that people would think if I have a pole light that I don't want to have the ground there, that I'll just, because it makes a connection to the earth. Okay, we don't care about the lightning. We don't care about, what do we care about the lightning for? We're trying to dissipate it to the earth, but we're never going to sit there and stand on. When you're working on it, you're not going to be working on it during a lightning storm. I hope not, anyway. I mean, that would be my hope. So nothing in the National Electrical Code requires me to put ground rods at pole lights, but an engineer might require it, right? So, and why are they requiring it? Because in case it does strike it, instead of having potential current come into the building, remember, it's going to, electricity takes all, you know this old saying that people had that said electricity takes the path of least resistance? Have you heard that? You've bound to have heard that. You know that's wrong, right? It's wrong in a sense that it takes all available paths, but it does so proportionally to the impedance or resistance of that path, right? So if the resistance is really high, less current will travel on that path. If the resistance is really low, more current will travel on that path. But it will travel on all paths in an attempt to get back to the source. Now, in a sense of lightning, when it hits a pole and it's going to the earth, it's not trying to get back to its source, although we have step ladders and leaders and all that. But in conventional thought, all it's trying to do is get to the earth. All right? Now, I mean, we won't get into the theory of whether it's actually striking up or striking down or whatever like that. We know that lightning is not trying to get back to our electrical system, so makes sense, right? Connect it to earth. Okay. That's fine. And a lot of engineers want that on the poles. Okay. But that's supplemental. That's fine. I can do that if I want. Okay? And that's fine. But when it comes to the safety of the circuit, then we want to make sure that, that we're providing an equipment grounding conductor. Okay? Now, you're saying, now I'll remind you also, Robbie, I serve on code making panel 5, so I would argue with you until this, and I can 100% tell you that you would be wrong. Not that I'm a know-it-all, but I serve on that panel, and I'm very intimate in it. Nothing is going to take the place of an equipment grounding conductor. Does not make it safer in those pole light scenarios. Okay? So, and it's not about a smarter thing. It's just about the concept of grounding and bonding, the whole concept of it. Okay. So if I've got a pole out there, what am I more at risk of? Being struck by lightning, or am I more at risk of working on that pole or coming in contact with a metal pole, or that I could get electrocuted? That's more the hazard, right? You would agree? So in that scenario, we have to have an equipment grounding conductor to that scenario. Okay, we can't just take a pole and just drive ground rods and put next to it and say done, right? We can't do that because, again, we would never clear an overcurrent device. The earth is too high, and it says right there on the screen, you see it? It says the earth shall not be considered an effective ground fault current path, right? And since it says that the earth cannot be used as that, here's what it says that is an effective ground fault current path. It's an electrical equipment and wiring and other electrically conductive material likely to become energized shall be installed in a manner that creates a low impedance circuit facilitating the operation of the overcurrent device or ground detector for high impedance grounded systems, which we could argue that they're not really grounded systems because they use a high impedance resistor in there, so it's not technically connected with ground, but we call it that, so we get away with it. It says it shall be capable of safely carry the maximum ground fault current likely to be imposed on it from any point in the wiring system where the ground fault occurs to the electrical system source. The electrical system source. And again, reminds us the earth cannot be considered that path. The earth's resistance is just too high. So the ground rods and everything that's put out there does not make it safer when it comes to me coming in contact with it. If you think that me getting energized and have it current hitting the metal enclosure or the metal pole going down to the earth, coming back on the earth over to the source through the grounding electroconductor, through the ground rods up into the panel to get back to the source to clear the breaker, if you think that's going to happen, never happen. Ever. Just can't happen. It can happen. I mean, that's only 4.8 amps. That won't trip a 15 amp breaker at all, ever. So it would just be impossible to do it. Okay. My thoughts. Let's see. My thoughts on renaming the equipment grounding conductor, the equipment bonding conductor. Nope. That's a gentleman in Florida's desire. And it is not my desire. I don't think it's necessary because it actually, everybody knows is equipment grounding conductor. And yes, it's a bond. It serves as a bonding conductor as well, but I think we know that. And there's an informational note underneath it that kind of explains that to us. So I don't necessarily think, would it bother me? No, it wouldn't bother me, but I don't necessarily think it's needed. Is it an equipment grounding conductor? Yeah. It connects all the equipment that plugs into it to the ground. It does, because it's all intimate. Now, here's the funny thing, William. The moment that we changed it to equipment bonding conductors, 5 years from now, somebody will say, wait a minute, Doesn't that create everything at the same potential? It puts everything at the same potential. It's with the grounding with the earth. So because we call what grounding terminals, we call as all these things to do with grounding, the terminals that these things screw into. So somebody will come along and try to get it changed back to equipment grounding conductor. They both do the same thing. So I don't know. I don't think it's worth changing. It's certainly not a sword I'm going to dive on, and I'm on that code panel, and I'm not diving on that sword because I don't think it's necessary. It doesn't cause confusion for me, but some people it might. But I don't know. You wanted my thoughts on it. That's my thought. I don't think it's necessary. But I mean, if they did it, I wouldn't. It wouldn't break my heart. But the problem with it, you still have to have some note. Because if I call it equipment bonding conductors, it literally does connect all the way. It is that, but is it not also for grounding as well? Yes, it is for grounding. So I think of bonding as tying pieces together, and it does that. But I also think about when things have to be at the same potential as Earth and everything comes back to the main bus and the main bonding jumper in here. We bring it all back together, everything. And it has the grounding electroconductors that go down to the grounding electrodes and all that. Then it is also grounding. Okay? So, and another interesting thing, William, is that we would have to fundamentally look at how we do the code, because we have a bonding section. I mean, we have bonding parts of 250, and they have with grounding parts of 250, right? So we'd have to think of how I just don't know that's necessary. That's just my opinion. I think it serves pretty good the way it is. Okay. Bob Robbie says, because the grounding electrode also helps with lightning as well as personal safety. Explain to me how the grounding electrode is personal safety. Let me give you an example. I have a house that was built in 1965 that has no grounding electrode system. The house runs fine, circuits run fine, everything runs fine. It's 12240, everything runs fine. Okay? Everything's fine. It doesn't know the difference. Now, if lightning strikes that building and it doesn't have an ability to get to the earth, okay, but that's under a lightning strike scenario. Okay? I believe that the grounding electrodes serve a role. I believe we need them. I believe they're there. But I think it's mainly for lightning. I think it's mainly for transients from high voltage lines that could come in contact with low voltage line on the line side of your meter areas. It also, I think, connection to earth provides the voltage stabilization that's necessary to keep from voltage fluctuation. I don't know that all those necessarily translate into something that makes it personnel safety, but I do understand the concepts of why it's beneficial to the system. But I know that there's been plenty of houses that are fine and they don't have that grounding electrode system, and they've been utilized for quite a while without anybody having any problem with it. You know what I mean? But being the code is the requirement, then I want grounding electrodes and I want them done right and all that kind of good stuff. I definitely do. But I don't know that I would lump them, in that scenario. Lightning, it is dangerous, and yes, it can strike and all that good stuff and things like that. So that's why we make that reference to it. Yeah. But when I've got a pole that's sitting out in the middle of the parking lot, probably not going to be personal safety. I'm not going to actually be on that pole when that happens. So, and the ground rods out there at a pole do not add to my personal safety. An equipment grounding conductor adds to my personal safety. So let's keep the two separate. You're not required to have electrodes at a pole in a parking lot. you are required to have it at a dwelling. That's where we have to draw the separation. Okay. Yep, and the only reason, Jay, that an engineer would want it is because they're worried about the concrete. They're worried about the concrete in a lightning strike being weakened, and so engineers love to put the ground rods there. And as an electrician, I just kind of smile and say, "Let's do it." I'm getting paid per ground rod, and I'm getting paid per, that jumping. And remember, that's not a grounding electroconductor. That's a supplemental conductor, right? So I mean, the code doesn't care what size that is. Heck, I could run 14 gauge to it if I want. Okay, it's supplementary. It's an additional. It's auxiliary, whatever we call it now. That's not the required one. That's not a requirement in the code. Let's see here. Two completely different areas, though the same. No, because I'm required to have one on the dwelling or the building. I'm not required to have one on the lamp poles. So, two difference. William says, yes, I agree with you, but I think the topic of grounding and bonding is a complex topic. I made a living off of it. And what is C in the field is a lot of confusion in sizing GECs and what needs to be bonded. All right, so that's the problem, William. The problem is people in the field are not studying the code. It's pretty simple to remember that you're not bothering me, Robbie. We just have a fundamental disagreement, and I serve on the code panel that could make that change, and we ain't going to do it. There you go. But in the gentleman in Florida can keep submitting it, it still ain't going to change. I'm just saying. Now, when it comes to the confusion, William, I think it's, really so here's the thing. For grounding electroconductor, you only have to remember 250.66. Everything else is bonding. Supply side bonding jumper, system bonding jumper, equipment bonding jumpers, all of that type of stuff. That is bonding. And that does have the bonding name behind it. So the easiest way to remember it is when sizing grounding electroconductors, that type of thing. Now, when it comes to equipment grounding conductors, I'm using a scenario here. So that's 250.66 for grounding electroconductors. That's grounding. Now, jump to 250.122. Equipment grounding conductors, always based on the size of the overcurrent protected device. Okay? Anything else is based on the size of the conductors, right? And that's when we do bonding jumpers and all that kind of stuff. All for bonding. All the bonding stuff is based on conductors. Whereas the equipment grounding is based on the overcurrent device. So that's kind of how I teach kids. But I shouldn't say kids. That's how I teach people to kind of, in their minds, separate the two. But I don't know that. Here's the thing, William. Even if I change the name of it, I've still got to size it the same way. I still got to do everything the same way. So I don't know. I like to think that this code book is for the technical person, and I want them to learn the difference personally. But I hear you. Submit that public input. We'll see how it's been submitted at least. Gosh, it's been submitted at least every code cycle for the last 3 or 4 that I've been on. Somebody has submitted it, and it makes it nowhere. But please submit it, and we'll look at it again. Oh, Robbie. Let's see here. Everything that is bonded, the equipment. I'm not even sure what you're saying there. Robbie, I don't know what you're saying. You're saying that, yeah, maybe you better stop, because I can't teach somebody that's not willing to listen. And I teach grounding and bonding. I Robbie, I wrote this book, which looks like it's transparent. I wrote this book, co-authored it on grounding and bonding. So I've extensively researched it over my 30 years in grounding and bonding. And I'm not discounting lightning. I get it. But there's a difference. You're making it sound like at a pole, you don't need an equipment grounding conductor. I don't care that you want to run a conductor over to a ground rod. Do it every day of the week. But do not think that that takes the place of an equipment grounding conductor, which is grounding. Okay? Grounding to the system. That can never be replaced with a ground rod. Never. And I did the math to prove it. We need to trip a breaker to turn the breaker off. If it's 25 ohms, and that's a perfect world for a ground rod, a perfect world. If it's 25 ohms and the circuit is a 120 volt circuit, that's only 4.8 amps. The 15 amp breaker is not going to trip until it goes over 15 amps or it overloads it for any continuous amount of time. It's never going to trip a breaker. It's an unsafe condition. The earth has too much resistance in it to be utilized as that low impedance path. And the code tells me right there on the screen, highlighted, you can't use the earth. You're required to make a low impedance effective ground fault current path. You do that through equipment grounding conductors. You don't do that through the earth. Ever. Ever. Just saying. That I can't, trying to make that as clear as I can. You know what I'm saying? So, that's what I'm saying. Now, if you want to put ground rods there, go for it. Is it going to help when lightning strikes and you do everything right and it allows it to dissipate out to the earth? Absolutely. But the ground rod that's being installed for that lamp pole is not for personal safety. That's simply for somebody that wants to preserve that base of that lamp and dissipate lightning strikes through the earth. They're not driving a ground rod in order to clear an overcurrent device. And that's what we're really trying to do with the equipment grounding conductor. Okay. Let's see here. I can't get the name here. Hold on. Let's see here. Hold on. I can't get the name. I'm scheduled to take my NEC exam pretty soon, but not a licensed electrician. Okay. However, what I don't get is why are your neutral conductors connected together to the grounding conductor in the panel? Okay, so it's required to do that at the main service disconnection means location. Okay, because they're tied together because you've got everything is trying to get back to the source. The source is the secondary side of the transformer, okay? So if I've time all together, so if I have a ground fault out in the circuit, and that is any ungrounded conductor, hot conductor that comes in contact with the metal or anything that's bonded, okay, then it gets back to the source on that equipment grounding conductor. Once it gets back to there, it's got to get over to the neutral to go back to the source to complete that circuit. Just like how you turn a lamp on with a switch. I have to complete it. So the only way to do that is to make that physical connection at one common location. And that's why we do it at the service. That's why we don't do it downstream at remote disconnects. We do it at the common location back at the service so that return current, it's still, remember, even a ground fault is still current. All that's still trying to complete the circuit, right? In a sense, okay? So again, completing that path, closing that circuit, we need to get it off the equipment ground, over to the neutral, back to the source, so that it can facilitate the operation of an overcurrent protected device. That's why we tie it together. Now, if you didn't bring those together, or in a main panel, you didn't put in a main bonding jumper, and you had a ground fault, and it comes back to the bus, and it can't get back over to the neutral to get back to the source to complete that circuit, then guess what happens? it stays energized and it creates a touch hazard. So that's why it's so important to have a main bonding jumper in the panel that's going to connect your equipment grounds and your grounded conductors, neutrals in most cases for dwellings or whatever. It's going to connect them together to complete that. Okay? And by making that circuit, you're creating a low impedance path. And again, remember what we said about current? It takes all available paths proportional to the path with the lowest impedance. So some will travel on the earth via your ground rods and a ground fault out at that pole, but the majority is going to travel on the equipment grounding conductor, and that's what's going to allow the overcurrent device to operate. Okay? But that's why we connect them together back at the service. Okay? Hopefully that answered that question for you. Let's see here. Again, Earth is never going to be the source, never going to be the path back to the source. I just showed you the code that said that. What is the main source of the ground as long as you don't connect at sub panels? So I guess I'm translating for you here. Downstream of the main panel, the reason we run 4 conductors, for example, and actually I have videos already out on grounding. Just go over to this channel. I've got plenty of stuff on grounding on here. You might have to go into the archives, but I got plenty of stuff on grounding. Already produced, already ready to watch. Or you could get the book. That book looks like it's transparent. All right. Let's see here. This book, Robbie, is available on. They're available on Amazon. If you email me, I'll send you a link to the book, and you can order it. It's actually a really good book. Me and Phil Simmons did this book. I don't know if you can see it, guys. There's some really good graphics in here. Me and Phil use the same graphic software. It's called CorelDRAW. And we go into really a lot. In fact, we go into this topic of why you can't use the earth and everything. And we have a really good graphic on it. I'm not sure where the heck it is, but we talk about the connections to the earth and why you have to have it, that type of thing. So, I mean, it's some really, really good stuff in here. We even go back in the beginning and explain the issue with the earth. And there you go. There you go, Robbie. Oops. Sorry about that, buddy. There. See that? You kind of can see it? That's a lamp post. And we got a ground rod next to it. And we talk about why it has to have an equipment grounding conductor and why that ground rod is not going to. Okay. See, it says lighting standard connected to a ground rod only. Violation. Okay. And that is I-4 figure. So if you look up in our drawing, and it's been a while here, it says a system or equipment can be grounded, connected to ground or earth and not be in compliance with the code rules. Figure I-4 shows a branch circuit that is extended to a metal pole that supports a parking lot luminaire. An equipment grounding conductor is not run with the circuit. A ground rod is installed at the pole to ground the metal pole and the luminaire. According to the definition of grounded, the metal pole and luminaire are in fact grounded because the installation is literally connected to the earth, as you were saying, as specified in the definition. However, the pole and the luminaire are not grounded properly and cannot be considered to be in compliance with the rules because an effective ground fault current path is required by 254A5 and 254B4 has not been provided. Okay? And so as seen in 250.4A5, the earth is not permitted to be used as the sole, only equipment grounding conductor. And as a result, it is not considered as an effective ground fault current path. Therefore, when we use the word grounded, we imply that a connection is being made to the earth or to a conductive body that serves to extend the earth connection in compliance with all applicable codes. So we want to connect it to the earth, but we're going to do that through the equipment grounding conductor back to the terminal, which goes to the grounding electroconductor, which goes down to the earth. Now, interesting with that, back to William, that would be problematic, right? To change the definition of an equipment grounding conductor when we're required to ground something per the code, whether we call something equipment grounding conductor or not, we're required to ground certain things as we're required to bond certain things. And so when it comes back to the panel and it ends up being connected with the earth through the grounding electrode and the grounding electroconductor, we're grounding. Yes, it's still serving a bonding role too. So, I mean, either way you were to switch that definition, we're going to have an asterisk because we need to tell people it does grounding too, because bonding is tying metal parts together. But we have to make a connection to the earth through the system to truly be grounded. And then we got a way to do that, okay? But the reason we're doing that back at the panel is so that we can clear an overcurrent device. That's deep stuff tonight. Deeper than I thought you wanted to go for exam prep. I can tell you that right now. And anyway, that book's available. Let's see. No problem, Ramiro. Anytime. Robbie should know that I'm not upset at him, that I just love to get excited and debate. I'm cool with everybody. But I tease a lot of people. And Danny was here, I'd be teasing the heck out of Danny, but I don't know where Danny is, and I'm worried that he's up in Oklahoma. I even sent him a message on Patreon, and he's a member of Patreon, and he hasn't responded yet, so I hope he's okay. He used to come into all these. Let's see. Oh, wait a minute. Robbie says, I want to say I just wasn't arguing with you because I know you are more knowledgeable. Don't worry about that, Robbie. I like debate. I don't take anything personal. I love debate. But I want to make sure that you take something away from it. Because I don't have a problem with you. I have a problem with you doing the ground rods. Most engineers require them. But just don't think that offers any personal safety, because it really doesn't. Be honest with you, even if it's a lightning strike, even if it was connected to earth and you were right there near it, I don't know how much personal safety it would provide for that either, because you're right there near it. So, anyway, good stuff. Let's see here. So remote distribution panel, just keep the equipment grounds away from the grounded conductor or the neutral in most cases for dwellings and whatnot, and keep them isolated. Okay. So usually in a remote panel, you'll take you can still use the make a connection. The neutral needs to float, and then the equipment grounds will connect to the case. So you use SCR cable, which is 4 conductors, or you do a raceway, you pull your 4 conductors or whatnot. Or you could pull 3 conductors in a EMT, for example, and then of course the EMT is your equipment grounding conductor. That would work too. And that's a big one that people, if you screw up a box fill calculation and you're using a metal raceway and you screwed it up and your engineer says that you got to pull an insulated equipment grounding conductor in there, but you're using EMT or rigid or whatever, and somebody screws up. Here's a funny story. If the engineer screwed it up and there was 4 conductors in there, 2 hots, a neutral, and a ground, and he screwed it up, he's going to be real quick to be able to allow you to not put that equipment grounding conductor and use in the metal raceway as an equipment grounding conductor under 250-118. He's going to be real quick to allow that because he screwed up. If it's on the other foot and you screw it up, then he's going to say, nope, I want that equipment ground in there. So whoever screws it up is probably the one that's going to be okay with it. But again, if the engineer designed it, then it's on them. So it's all good, Robbie. It's all good. All right, guys. Well, that's 11:30. I think I started at 8. Wow, another marathon. We covered a lot of topics tonight in that 3 hours and 40. We covered a lot of stuff. We covered pull boxes. We covered optional methods. I answered a bunch of different questions. We got to wrap back and forth and grounding and bonding, which I love to do, by the way. My favorite topic in the world is grounding and bonding. or bonding and grounding, or however the flavor is of it today. And hopefully I answered your question, William, on my thought. Again, I understand sometimes it makes things easier for people, but usually I tell them they probably make it more confusing because they're not in the code like they should be. If you're in the code, then it really shouldn't be too confusing, right? Anytime we're doing grounding, equipment grounding conductors, we know 250-122 based on the overcurrent device. Pretty simple. Grounding electroconductors based on the size of the service conductors, 250.66. Pretty straightforward. Bonding jumpers, supply side bonding jumpers, grounded conductors. First, we have to calculate the unbalanced loads in a neutral conductor like we did earlier. And we have to compare it to 250-102C. And we have to, whatever results in the larger of the two, we take that and we run with it. Anything else? Supply side bonding jumpers, all of that's going to be based on the size of the conductors. Okay? So it's kind of one of those things where we went all over the place today. I think it was a good show. The question people will ask me now is, am I going to upload this one for people to watch later? I don't know, because I just don't think people will re-listen to 3 hours and 44 minutes. I just don't think they will. So it's also the benefit of those that come and hang out with me, that you get to have it. Why should those other people that don't get to have it? You get it. You got to ask questions. You know, sometimes that's how I look at it too. Ramiro, I'm usually in here at least once a week, every week. And of course, my Saturday night show, which is live at 8 p.m. Central Standard Time on same channel. It's Electrician Live. And this week's topic is service bonding. So you want to check that out if you want to get learn about service bonding. Now, it's probably going to be redundant to you if you watched my video or listened to my video or whatever I did podcast. I don't remember on 250.92 and all that I did a couple weeks ago. It's very similar to that. But I've got some images and graphics and stuff like that. And I've done service bonding before on my channel. So again, but Electrician Live is for people that don't really know about the channel yet. So that's why we're doing that topic, and I'm going to do service bonding. Okay. But anyway, Tim, you're out of here. Thanks for hanging around. I'm about to go too, guys. I didn't realize, really, it's amazing. It is amazing how time flies when we all are having fun. You know what I'm saying? I can't believe it. It's 3 hours and 45 minutes that we did this stream tonight. Wow. My wife is hating me in there. I can tell you right now, because I worked all day and then I got on with this all night. She's not happy. Here it is, almost midnight. Anyway, hey guys, I appreciate all of you. Thank y'all for coming in here. Hopefully I didn't offend anybody. I was just playing with you back and forth. So that's how I like to do it. Every educator's different. I'm not like other educators. I do my own thing, and I just like to help. And hopefully I helped you out. And if any of that I said tonight confused you in any way, email me at info at masterthenec.com. And in the next show, I will clarify. How about that? I don't mind. Like, I don't mind being wrong. I don't mind. Just teach me why I'm wrong. That's all I want. If you're willing to teach me, there you go. I will convey that message to all the people that listen. Okay? I appreciate all of y'all. God bless. And until next time, stay safe. And a lot of people are getting back to work, and this COVID thing is starting to relax up a little bit. People are starting to get out. You know what I'm saying? But don't go out and get COVID. Okay, don't go get the coronavirus. You know, now that everybody's itching to get out and to do things and all. Don't get all itchy and go out now. I mean, I believe we all have to get back to work, but just be careful. Social distance is still the word that we didn't know what it was until now we know what it is, and I think we know what it is. Okay, be honest with you. I've been married for 30 years. I feel like I've been social distancing my whole life. I'm just saying. All right. Till next time, folks. Stay safe. God bless. I appreciate all of y'all. You've been listening to Electrician Live with your host, Paul